Welcome to Gnana Taranga. This program is sponsored by Department of Pre-University, Government of Karnataka. This is Achyuta, lecturer in physics, VVS Sardar Patel PU College, Bangalore. Today we shall actually discuss two chapters of first year PUC, that is laws of motion and work energy theorem. So we shall first see some synopsis of this and then later on solve few problems based on this. So to start with, we will go with laws of motion. Previously we also had done synopsis of for some of the first year topics, that is units and dimensions, motion in one dimension and motion in two dimension. Here we actually described motion, but now with respect to Newton's laws of motion and work energy theorem, here we are going to find out what is the cause for this particular motion. And the cause for the motion is basically force. And what is force? It may be defined as an agency, a push or a pull which changes or tends to change the state of rest or of uniform motion or the direction of the motion of the body. Force is basically a vector quantity. So when the force is applied, three things can actually happen. There can be a change in the speed, there can be change in the direction, or there can be change in the shape of the object. So there are two kinds of forces. You have a positive force and you have a negative force. When you call about positive forces, that is, let us say we have interaction between two charges. If two charges are the charges are different, then you basically have a repulsive force, and this is termed out to be a positive force. When there is an attraction, in case of masses with respect to gravitational forces, then this kind of force is called as a negative force. So we shall see further. So the prime idea with respect to motion of an object is basically the inertia. It is an inherent property of a material body by virtue of which it cannot change by itself its state of rest or of uniform motion in a straight line. So there are three kinds of inertia here: inertia of rest, inertia of motion, and inertia of direction. So in case of inertia of rest, let us say a person is standing in a bus, falls backward. When the bus stops suddenly, he falls backwards. He was actually in rest, and because there was a brake applied, so he actually moved in the forward direction. So this is basically an example of inertia of rest. When the bus stops, when the same bus which is actually moving stops, person comes in the forward direction. Why? Because the person was actually have a tendency of moving in the tendency of motion, and therefore because of inertia of motion, the person experiences a forward motion. In the third case, that is inertia of direction, let us say we are traveling in a vehicle and then we take a curved path. So when the car takes a turn, you tend to move in the other direction. Okay, so this is basically an example for inertia of direction. So how else can you actually define this inertia? Mass is basically a measure of inertia. If a body has more mass, it has more inertia. That is, it is difficult to change its state of rest or of uniform motion. Heavier mass would actually have a greater inertia. So keeping this in mind, if you can actually combine the Newton's second law and the Newton's third law, we actually discuss the concept of momentum. So we shall discuss that later on, but still let me make a definition of what exactly momentum means. It is a quantity of motion in a body. It is equal to the product of mass and velocity. Momentum is a vector quantity having a direction of velocity. So momentum, the direction of the momentum is in the direction of the velocity. The SI unit of momentum is kg per meter per second, and in CGS it is gram per centimeter second. So coming to the main part of this particular discussion, that is the description of motion, is something that you have already studied in the first year. And now we shall actually see what is the cause for such kind of a motion. And Newton formulated few laws to understand the motion in everyday life. So the Newton's first law, which states that every body continues to be in state of rest or of uniform motion along a straight line unless an external force is applied to change that state or otherwise. So, let me give an example here. When a bus suddenly starts moving, the passenger sitting inside falls backwards. So, when you have dust removed in a hanging carpet by beating it with a stick, so the dust is there, you take a stick and hit it and the dust actually falls down. So, in all these cases we are actually discussing, and the first particular Newton's law actually talks about the existence of force. Without force you cannot actually have the body moving. So, that is basically the Newton's first law of motion. So, coming to the second law, it states that the rate of change of momentum of a body is directly proportional to the applied force, and the change in momentum takes place in the direction of the applied force. This law gives the measure of force. In the first law we actually talked about the definition of force. Now in the second law we talk about the measure of force. So force is measured in terms of Newton, and how this measure is actually done we shall see here. To put it mathematically, the force is rate of change of momentum. Momentum, as I discussed earlier, is mass into velocity. So that change in velocity dv by dt is equal to nothing but m into a. This is what we famously use as force is equal to mass into acceleration. And this acceleration, from the equations of motion we know that v is equal to u plus at. So you can take that a, therefore a would be v minus u divided by t, where v is final velocity and u is the initial velocity, and therefore the change in velocity into mass would give us the force. So when m is constant v changes and v is constant m changes. In both the cases you can actually have force. So force is proportional to mass, force is proportional to acceleration, and therefore force is equal to some proportionality constant times mass into acceleration. This proportionality constant is purposely made equal to unity so that we can explicitly use the definition of the measurement of SI unit of force as Newton. So you can see here in the example A, F I told you is proportional to acceleration, is also proportional to mass. In all the three cases here we shall keep the mass constant, and then when a force is applied you have a corresponding acceleration with respect to the force that is actually applied. In the second case, that is example B, you would actually see that in the spring system there, when you apply the twice the force as you applied in the case A, the acceleration here will be twice. Similarly, when the force is half the force in the first case, the acceleration turns out to be half the acceleration in the first case. So the very famous law of the Newton's laws is actually the Newton's third law of motion. It is actually the Newton's third law which should actually be stated first, but anyway, in the in textbooks we actually study this as third law. It states that for every action there is an equal and opposite reaction. Mathematically, if a body is exerting a force, if there are two bodies and body A is exerting force on body B, and similarly equal and opposite forces are exerted by body B with respect to A, and this is what is written as the force BA is equal to minus force AB. And this force, that is a Newton's in case of Newton's third law, force of action and reaction never cancel out because they act on different bodies, they do not act on the same bodies. If at all they would have acted on the same bodies, these forces would have actually got cancelled out. So because it should not get cancelled out there, so we actually have these forces acting on two different bodies. This is something that is to be remembered. So the SI unit of force, as I stated earlier, is Newton, and in CGS unit we call it as dyne. And what is 1 Newton? 1 Newton is 1 kg per meter per second square, and 1 dyne is 1 gram and 1 centimeter per second square. 1 Newton is 10 power 5 dyne. This is something that you have actually derived in units and dimensions. And then for all our day-to-day purposes, the force that we actually experience is basically the gravitational force. The SI unit of force is kilogram weight or kilogram force also it is called as. In CGS units, it is gram weight or gram force. 1 kg weight or 1 kg force is 1 kg into 9.8 meter per second square, which is 9.8 Newton. Then how is that if I actually have to get 1 Newton force on a weighing machine, how much should the weighing machine actually show? If you can actually make a reverse calculation, you could actually see, because earlier when we actually stated in the previous case, you can see here, I said 1 Newton is 1 kg into 1 meter per second square. So here in this case, the acceleration turns out to be 9.8 meter per second, unlike 1 meter per second square. So so it so happens that you have to substitute this, and therefore you will actually see to get a force of 1 Newton, the weighing machine, on the weighing machine, if you actually add 100 grams, then you will actually have 1 Newton force, and that's because of the value of G. So we actually use impulse also in some places for force. And what is force? Impulse is what is impulse? Impulse is a total effect of a large force. That is, when a huge amount of force is acting on a very short interval of time, then they produce a finite change in the momentum. It is defined as the product of force and the time for which it acts, and equals to total change in momentum. Impulse is force into the time duration, and that time duration is very, very small, and therefore the total change in momentum is basically impulse in this particular case. So impulse, as in the case of force, is also a vector quantity, and it is written there as actually J there. It should actually be written as I, and it should be actually J. Vector J is integral T1 to T2 F dot dt, where dt is this small interval that we were actually talking about, and area under the force time graph will actually give us the momentum. You can actually see here, this momentum is m is equal to v minus u. The SI unit of impulse, unlike force, not Newton but Newton second, or this is kg meter per second. In CGS units, it is gram centimeter per second. So coming back to the law of conservation of linear momentum. In the absence of an external force, vector sum of linear momenta of a system of particles remains constant. So if there are n number of momentums due to collision with respect to the body, the total momentum is basically conserved, and that is what this is basically telling us. When two bodies collide, the total momentum before collision is equal to total momentum after collision. You can actually see here, this can be formulated as m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So now let us actually see a small demonstration of this law of conservation of linear momentum. Okay, I was telling you about one of the examples, a demonstration on explain the conservation of linear momentum. This is a very famous Newton's cradle instrument for the simple demonstration. You can actually see there are 5 masses here, and I shall they are all connected via a thread here, and then I shall pull out one of this. ನೋಡಿ ಇದನ್ನು ತಗೋತೀನಿ ನಾನು. ಇದನ್ನು ತಗೊಂಡು ನಾನು ಇಷ್ಟು ದೂರದಿಂದ ಬಿಟ್ಟರೆ ಆಮೇಲೆ ಇಲ್ಲಿ ಎಂಡಲ್ಲಿ ಇರುವಂಥ ಇನ್ನೊಂದು ಮಾಸು ಅಷ್ಟೇ ದೂರಕ್ಕೆ ಮುಂದೆ ಬಂದಿರುತ್ತೆ. ಅಂದರೆ ಇನಿಷಿಯಲ್ ಮೊಮೆಂಟಮ್ ಏನಿತ್ತು, ಇಲ್ಲಿ ಫೈನಲ್ ಮೊಮೆಂಟಮು ಅದೇ ಆಗಿತ್ತು. ದೇರ್ ಫಾರ್ ದಿಸ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಥಿಂಗ್ ಇಸ್ ಆ್ಯಕ್ಚುಲಿ ಕನ್ಸರ್ವ್ಡ್. ಸೊ ಇವಾಗ ಸಪೋಸ್ ನಾನು ಇದ್ರದ್ದು ಡಿಸ್ಟೆನ್ಸ್ನ ಇನ್ನೂ ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಮಾಡ್ತೀನಿ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ. ಸೊ ಇನ್ನೂ ಜಾಸ್ತಿ ಮಾಡಿದ್ರೆ ಇಟ್ ಹ್ಯಾಸ್ ಆ್ಯಕ್ಚುಲಿ ಟ್ರಾವೆಲ್ಡ್ ಎ ಗ್ರೇಟರ್ ಡಿಸ್ಟೆನ್ಸ್. ಸೊ ಇವಾಗ ಏನಾಗುತ್ತೆ, ಇದೂ ಅಷ್ಟೇ ಡಿಸ್ಟೆನ್ಸ್ ಟ್ರಾವೆಲ್ ಮಾಡಿದ್ರೆ ಅವಾಗ ದೆನ್ ವಿ ಕ್ಯಾನ್ ಆ್ಯಕ್ಚುಲಿ ಸೇ ದಟ್ ದಿ ಮೊಮೆಂಟಮ್ ಇಸ್ ಬೇಸಿಕಲಿ ಕನ್ಸರ್ವ್ಡ್. ಶಲ್ ವಿ ಇಫ್ ವಿ ಕ್ಯಾನ್ ಆ್ಯಕ್ಚುಲಿ ಮೂವ್ ಫರ್ದರ್, ಇದನ್ನು ಸುಮ್ಮನೆ ಮುಂದೆ ತೊಗೊಂಡು ಹೋಗೋದಾದರೆ, ಇವಾಗ ನಾನು ಒಂದೇ ಒಂದು ಮಾಸ್ ಇರೋ ಬದಲು 2 ಮಾಸನ್ನು ಈ ಕಡೆಯಿಂದ ತೊಗೊಂಡ್ರೆ ನಾನು ಇಲ್ಲಿ ಎಷ್ಟು ಮಾಸ್ ಹೋಗುತ್ತೆ ಅಂತ ಪ್ರಶ್ನೆ ಮಾಡಿದ್ರೆ ವಿ ಶಲ್ ಆ್ಯಕ್ಚುಲಿ ಸಿ ಏನಾಗುತ್ತೆ ಅಂತ. ಯು ಕ್ಯಾನ್ ಆ್ಯಕ್ಚುಲಿ ಮೇಕ್ ಎ ಗೆಸ್. ನೋಡಿ, ನಾನು 2 ತೊಗೊಂಡಾಗ 2 ಹೋಗುತ್ತೆ, ಯಾಕೆಂದರೆ ಮೊಮೆಂಟಮ್ ಈಸ್ ಬೇಸಿಕಲಿ ಕನ್ಸರ್ವ್ಡ್ ಇಯರ್. 2 ತೊಗೊಂಡ್ರೆ ಇಲ್ಲಿ 2 ಹೋಗುತ್ತೆ, ದಟ್ ಈಸ್ ಸಮಥಿಂಗ್ ವಿಚ್ ಕ್ಯಾನ್ ಬಿ ಅಂಡರ್ಸ್ಟುಡ್. ಆದರೆ ಇಲ್ಲಿರೋದೇ ಟೋಟಲ್ 5 ಮಾಸ್ ಇದೆ. ಇವಾಗ ಸಪೋಸ್ ನಾನು 3 ಈ ಕಡೆ ತೊಗೊಳ್ತೀನಿ ಅಂತ ಇಟ್ಕೊಳ್ಳೋಣ. ಅವಾಗ ಇಲ್ಲಿ ಎರಡೇ ಇದೆ. ಹಾಗಿದ್ರೆ ಈ ಎರಡು ರಿಮೈನಿಂಗ್ ಮಾಸಸ್ ಏನಿದೆ ಇನ್ನೂ ಜಾಸ್ತಿ ದೂರ ಹೋಗುತ್ತಾ ಅಥವಾ ಮೂರು ಬರುತ್ತಾ? ಮೂರು ಬರೋಕ್ಕೆ ಇಲ್ಲಿ ಮೂರು ಮಾಸ್ ಇಲ್ಲ, ಇಲ್ಲಿ ಎರಡೇ ಇರೋದು. ಇನಿಷಿಯಲ್ ಮೊಮೆಂಟಮ್ ಈ ಮೂರು ಮಾಸ್ ಕಡೆಯಿಂದ ಇಲ್ಲಿ ಬಂದು ಇದನ್ನು ಹೊಡೆದ್ರೆ ಇಲ್ಲಿ ಎರಡೇ ಇರೋದು. ಹಾಗಿದ್ರೆ ಇದು ಮೊಮೆಂಟಮ್ ಕನ್ಸರ್ವ್ ಆಗಬೇಕಾದ್ರೆ ಇದು ಜಾಸ್ತಿ ದೂರ ಹೋಗಬೇಕು ಅಂತ ನಿಮ್ದೊಂದು ಗೆಸ್ ಇದ್ರೆ ವಿ ಶಿಲ್ ಆಕ್ಚುಲಿ ಸಿ ವಾಟ್ ವುಡ್ ಆಕ್ಚುಲಿ ಹ್ಯಾಪನ್. ಈಗ ನೋಡಿ, ನಾನು ಮೂರನ್ನ ಈ ಕಡೆ ತಳ್ತೀನಿ, ನೋಡಿ ಮೂರು ಹೋಗುತ್ತೆ. ಬೇಸಿಕಲಿ ಮೊಮೆಂಟಮ್ ಇಸ್ ಕನ್ಸರ್ವ್ಡ್, ಅದಕ್ಕೋಸ್ಕರ. ಸೊ 4 ತೆಗೆದ್ರೆ ಈ ಕಡೆನೂ 4 ಹೋಗುತ್ತೆ. ಇದರಲ್ಲಿ ಇನ್ನೂ ಒಂದು ಸ್ವಲ್ಪ ಇಂಟ್ರೆಸ್ಟಿಂಗ್ ಥಿಂಗ್ಸ್ ಮಾಡ್ಬೋದು ಟು ಚೆಕ್ ದಿ ಲಾ ಆಫ್ ಕನ್ಸರ್ವೇಷನ್ ಆಫ್ ಮೊಮೆಂಟಮ್. ಸಪೋಸ್ ನಾನು ಈ ಕಡೆಯಿಂದ ಒಂದು ಮಾಸು ಈ ಕಡೆಯಿಂದ ಒಂದು ಮಾಸ್ ತಗೊಂಡಿರ್ತೀನಿ, ಇದೆರಡನ್ನು ಕೊಲೈಡ್ ಮಾಡಿದ್ರೆ ಇವಾಗ ಮೊಮೆಂಟಮ್ ಕನ್ಸರ್ವ್ ಆಗಬೇಕು. ಇದು ಬಂದು ಸುಮ್ಮನೆ ಇದನ್ನು ಹೊಡೆದು ಹಾಗೆ ನಿಂತ್ಕೊಂಡ್ಬಿಡುತ್ತಾ ಅಥವಾ ಏನಾಗುತ್ತೆ ಅಂತ ನೀವು ಒಂದು ಪ್ರಶ್ನೆ ಮಾಡ್ಕೊಂಡ್ರೆ ಯು ಕ್ಯಾನ್ ಆಕ್ಚುಲಿ ಸಿ ಹಿಯರ್. ಸೊ ಏನಾಗ್ತಿದೆ, ಇದು ಬಂದು ಹೊಡೆದಾಗ because of this force this is moving this side, because of this force this is actually moving in the other direction. ಇವಾಗ ನಾನು ಒಂದ್ ಕಡೆಯಿಂದ ಎರಡು ತಗೋತೀನಿ, ಇನ್ನೊಂದು ಕಡೆಯಿಂದ ಒಂದೇ ತಗೋತೀನಿ. ಅವಾಗ ನೋಡಿ ಆಲ್ಟರ್ನೇಟ್ ಆಗಿ ಒಂದು ಮಾಸು ಒಂದ್ಸತಿ ಎರಡು ಕಡೆಗೆ, ಇನ್ನೊಂದ್ಸತಿ ಇನ್ನೊಂದು ಮಾಸು ಒಂದ್ ಕಡೆಗೆ ಮಾತ್ರ ಮೂವ್ ಆಗುತ್ತೆ. So you can actually see that. So this is a very nice demonstration to understand the law of conservation of momentum, which is basically valid. Here we can take one more example. The momentum conservation the ಇನ್ನೊಂದು ಎಕ್ಸಾಂಪಲ್ ತಗೊಳ್ಳೋದಾದ್ರೆ, when a bullet of mass m is fired with a velocity v from a gun of mass m, the gun recoils with velocity v. So momentum of the gun is equal to momentum of the bullet. So ಅವಾಗ recoil of velocity of the gun, ನಾನು ಬುಲೆಟ್ ಹೊಡೆದಾದ್ಮೇಲೆ ಗನ್ ಹಿಂದೆ ಬರುತ್ತಲ್ಲ, ಆ ಹಿಂದೆ ಬರುವಂತ ಇಲ್ಲಿದೆ ನೋಡಿ, ಹಿಂದೆ ಬರುವಂತ ವೆಲಾಸಿಟಿ ಇದೆಯಲ್ಲ, ಈ ವೆಲಾಸಿಟಿನ I can actually calculate. That velocity v will be equal to minus mv divided by m by using the law of conservation of linear momentum. So ಇನ್ನೊಂದು ಎಕ್ಸಾಂಪಲ್ ತಗೊಳ್ಳೋದ್ರೆ ರಾಕೆಟ್ ಪ್ರೊಪಲ್ಷನ್ ತಗೊಳ್ಳಿ. It is an example of momentum conservation in which large backward momentum of ejected gases imparts an equal forward momentum to the rocket. ಹಿಂದೆ ಬರುವಂತ ಎಕ್ಸಾಸ್ಟ್ ಗ್ಯಾಸಸ್ ಏನಿದೆ ಅದು ರಾಕೆಟ್ ಅನ್ನ ಮುಂದೆ ಪುಷ್ ಮಾಡುತ್ತೆ. Due to the decrease in mass of the rocket fuel system, the acceleration of the rocket keeps on increasing. ಇದು ವೇರಿಯಬಲ್ ಮಾಸ್ ಸಿಸ್ಟಮ್. ಇದು ಅದಕ್ಕೆ ಇಲ್ಲೊಂದು ಸಣ್ಣ ಎಕ್ಸಾಂಪಲ್ ತರ ಕೊಟ್ಟಿದ್ದೀನಿ. ಇಲ್ಲಿ ನೋಡಿ, ಒಂದು ಗಾಡಿ ಇದೆ, ಅದರಲ್ಲಿ ಮರಳಿದೆ, ಕೆಳಗಡೆ ಒಂದು ಹೋಲ್ ಇದೆ. ಸೊ ಹಾಗಾಗಿ ಈ ಹೋಲಿಂದ ಮರಳು ಕೆಳಗಡೆ ಬೀಳ್ತಾ ಇರುತ್ತೆ. ಸೊ ಈ ಗಾಡಿ ಹೀಗೆ ಮೂವ್ ಆಗ್ತಿದೆ ವಿತ್ ಸರ್ಟನ್ ವೆಲಾಸಿಟಿ. ಇದು ಹೋಗ್ತಾ ಇರಬೇಕಾದ್ರೆ ಇಲ್ಲಿ ಏನಾಗಿದೆ, ಅದು ಮುಂದೆ ಹೋಗ್ತಾ ಹೋಗ್ತಾ ಈ ಮರಳು ಇದ್ರ ಕೆಳಗಡೆ ಬರ್ತಾ ಇದೆ. ಹಾಗಾಗಿ ಈ ಸಿಸ್ಟಮ್ ಏನಿದೆ, ಈ ಸಿಸ್ಟಮ್ದು ಮಾಸ್ ರೆಡ್ಯೂಸ್ ಆಗ್ತಾ ಇದೆ. ಸೊ ಹಾಗಾಗಿ ಇವಾಗ ಇದ್ರದ್ದು ವೆಲಾಸಿಟಿ ಹೇಗಿರುತ್ತಪ್ಪ ಅಂತ ನೀವು ನೋಡಿದ್ರೆ, ದಟ್ ವೆಲಾಸಿಟಿ ವಿಲ್ ಬಿ ವಾಟ್ ಎವರ್ ಇಸ್ ದ ಇನಿಷಿಯಲ್ ವೆಲಾಸಿಟಿ log e to m naught divided by m. This is the ratio of the initial mass of the system and the change in the mass. ಈ ಮರಳು ಹೋಗ್ತಾ ಇದೆ, so therefore the mass of the system doesn't remain the same. So this is exactly a consequence of what actually happens in the rocket propulsion. So this is basically a variable mass system. ಮುಂದೆ ನೋಡೋಣ. So concurrent forces. The forces acting at the same point of a body are called concurrent forces. So equilibrium of concurrent forces andre enandre, a number of concurrent forces acting on a body are said to be in equilibrium if their vector sum is 0 or if their forces can be completely represented by sides of closed polygon taken in the same order. Yenidu idra consequence eno we can actually see later. See nodi, if there are many number of forces which are actually acting on a system, if the net force is actually equal to 0, il nodi, there are so many forces F1, F2, F3 and Fn, and then if all the net force of all this is actually equal to 0, then it is said that the body is actually in equilibrium and therefore the body will not be accelerating here. The forces are acting no doubt, but the body is not actually accelerating because for one force there are other forces which are actually acting which are neutralizing the effects of the earlier force. So you can actually see as a consequence of what we discussed earlier, the Lami's theorem. ಈ ಥಿಯರಮ್ ತುಂಬಾ ಹೆಲ್ಪ್ ಆಗುತ್ತೆ ನಮಗೆ ತುಂಬಾ ಪ್ರಾಬ್ಲಮ್ ಸಾಲ್ವ್ ಮಾಡೋದಕ್ಕೆ. ಇಟ್ ಸ್ಟೇಟ್ಸ್ ದಟ್ ಇಫ್ 3 forces acting on a particle keeps in equilibrium, then each force is proportional to the sine of the angles between the other 2 forces. If alpha, beta, gamma be the angles between F2, F3, F3, F1, F1, F2 respectively, then according to Lamens theorem, ನೋಡಿ ಇಲ್ಲಿ Lamens theorem ಇಂದ ನಮಗೆ ಈ ಈಕ್ವೇಷನ್ ಸಿಕ್ಕಿದೆ. ಅದರ ಅರ್ಥ if this is the angle, so if this is the force F1 and let us say if this is force F2 and if this is force F3 which are actually acting, then the ratio of these two forces with respect to this force, the sign of the Lamens theorem says that this force F1 is equal to the sign of the angle between the other two forces. Similarly, you can actually consider this ನೋಡಿ ಇಲ್ಲಿ F3 F1 ಇದೆ, therefore this is beta and let us say this is gamma. So this is what is basically the Lamens theorem actually telling us. So one of the very main concepts of laws of motion, ನೀವು ಲಾಸ್ ಆಫ್ ಮೋಷನ್ ಏನಕ್ಕೆ ಕಲಿಬೇಕು ಅಂತ ಕೇಳಿದ್ರೆ, ಲಾಸ್ ಆಫ್ ಮೋಷನ್ ನಾವು ಏನಕ್ಕೆ ಕಲಿಬೇಕು ಅಂದರೆ ಟು ರೈಟ್ ಫ್ರೀ ಬಾಡಿ ಡಯಾಗ್ರಾಮ್. ಸೊ ದಿ ಮೇನ್ ಐಡಿಯಾ ಆಫ್ ಲಾಸ್ ಆಫ್ ಮೋಷನ್ ಇಸ್ ಆಕ್ಚುಲಿ ಟು ರೈಟ್ ಫ್ರೀ ಬಾಡಿ ಡಯಾಗ್ರಾಮ್. ಯಾವುದೇ ಒಂದು ಸಿಸ್ಟಮ್ ಸಿಕ್ಕಿ ನಮ್ಗೆ ಅದರಲ್ಲಿ ಮೋಷನ್ ಹೇಗಾಗ್ತಿದೆ ಅಂತ ತಿಳ್ಕೊಬೇಕಾದ್ರೆ ನಮಗೆ ಫ್ರೀ ಬಾಡಿ ಡಯಾಗ್ರಾಮ್ ಬರೆಯಬೇಕು. ಇದನ್ನ ಫೇಮಸ್ ಆಗಿ ಕ್ಲಾಸಲ್ಲಿ FBD ಅಂತ ಕರೀತಾರೆ, ಅಂದರೆ ಫ್ರೀ ಬಾಡಿ ಡಯಾಗ್ರಾಮ್ ಅಂತ. ಏನಿದು? ಲೆಟ್ ಅಸ್ ಸಿ. ಎ ಡಯಾಗ್ರಾಮ್ ಫಾರ್ ವಿಚ್ body of the system showing all the forces exerted on the body by the remaining parts of the system is called free body diagram. ಏನ್ ಬೇಸಿಕಲಿ ಇದು ಅಂದ್ರೆ, ಇಲ್ಲಿ ನೋಡಿ ಈ ಒಂದು ಮಾಸ್ ಇದೆ, ಈ ಮಾಸು ಇಟ್ ಈಸ್ ಎಕ್ಸರ್ಟಿಂಗ್ ಎ ಫೋರ್ಸ್ ಇನ್ ದಿ ಡೌನ್ವರ್ಡ್ ಡೈರೆಕ್ಷನ್ mg. ಇದು mg ಫೋರ್ಸ್ ಡೌನ್ವರ್ಡ್ ಡೈರೆಕ್ಷನ್ ಎಕ್ಸರ್ಟ್ ಮಾಡ್ತಿದೆ ಅಂದ್ರೆ ಇದಕ್ಕೊಂದು ನಾರ್ಮಲ್ ಫೋರ್ಸ್ ಇನ್ ದಿ ಆಪೋಸಿಟ್ ಡೈರೆಕ್ಷನ್ ಇದೆ. ಫಾರ್ ದಿಸ್ ಆಕ್ಷನ್ ದೇರ್ ಇಸ್ ಎ ರಿಯಾಕ್ಷನ್ ಹಿಯರ್ ಅಟ್ ದಿಸ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಪ್ಲೇಸ್. ಸೊ ಆರ್ ರಾದರ್ ಯು ವಿಲ್ ನೋ ದಟ್ ದೇರ್ ಇಸ್ mg ಹಿಯರ್ because of the normal force. So ಅದೇ ತರ ಬೇರೆ ಬೇರೆ ಪ್ರಾಬ್ಲಮ್ ಅಲ್ಲಿ ಇಫ್ ಯು ಆರ್ ಟ್ರೈಂಗ್ ಟು ರೈಟ್ ದಿ ಫ್ರೀ ಬಾಡಿ ಡಯಾಗ್ರಾಮ್ ಆಫ್ ದಿಸ್, ಇಲ್ಲಿ ನೋಡಿ ಇನ್ನೊಂದು ಎಕ್ಸಾಂಪಲ್ ತಗೋಣ. ಇಲ್ಲಿ ಮೋಷನ್ ಆಫ್ ಕನೆಕ್ಟೆಡ್ ಬಾಡೀಸ್ ಇದನ್ನು ನೋಡಿರ್ತೀರ ನೀವು. ಸಪೋಸ್ ಟೂ ಬಾಡೀಸ್ ಆಫ್ ಮಾಸಸ್ ಕ್ಯಾಪಿಟಲ್ M ಅಂಡ್ ಸ್ಮಾಲ್ m, ವೇರ್ ದಿಸ್ ಕ್ಯಾಪಿಟಲ್ M ಇದನ್ನ ನಾನು M2 ಅಂತ ಮಾಡ್ಕೊಂಡಿದ್ದೀನಿ. ಇಲ್ಲಿ ಇದು ನೀವು ಕ್ಯಾಪಿಟಲ್ M ಅಂತ ಮಾಡ್ಕೊಳ್ಳಿ, ಇದನ್ನ ಬೇಕಾದ್ರೆ M ಅಂತ ಮಾಡ್ಕೊಳ್ಳಿ. ಆರ್ ಟೈಡ್ ಅಟ್ ದಿ ಎಂಡ್ಸ್ ಆಫ್ ಎನ್ ಇನ್ಎಕ್ಸ್ಟೆನ್ಸಿಬಲ್ string passing over a frictionless pulley, then the acceleration of the masses ಅಂತ ಕೇಳ್ತೀರ. ಇಲ್ಲಿ the acceleration of the masses ಇದನ್ನ ನಾನು ಮಾಡಬೇಕು ಅಂದ್ರೆ ಇಟ್ ಈಸ್ ವೆರಿ ಸಿಂಪಲ್. ನೋಡಿ ಈ ಸಿಸ್ಟಮ್ ಇಟ್ಕೊಂಡೆ ಹೇಳ್ತೀನಿ ನಾನು M2 M1 ಅಲ್ಲಿ. ಇಲ್ಲಿ ದಿಸ್ M2, ಈ M2 ಮಾಸ್ ಏನಿದೆ, ದಿಸ್ ಇಸ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸಿಂಗ್ ಎ ಡೌನ್ವರ್ಡ್ ಫೋರ್ಸ್ ಹಿಯರ್. ಸೊ ಅಂಡ್ ದಿಸ್ ಇಸ್ ಆಕ್ಚುಲಿ ಆಕ್ಸಲರೇಟಿಂಗ್ ಇನ್ ದಿಸ್ ಡೈರೆಕ್ಷನ್ ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ. ಸೊ ಈ ಜಾಗದಲ್ಲಿ ಇಫ್ ಯು ರೈಟ್ ದಿ ಈಕ್ವೇಷನ್ಸ್ ಆಫ್ ಮೋಷನ್, ಸೊ ಪ್ರತಿ ಸಲಿನೂ ನಾನು ಈಕ್ವೇಷನ್ಸ್ ಆಫ್ ಮೋಷನ್ ಮಾಡಬೇಕಾದ್ರೆ ಬಾಡಿ ಆಕ್ಸಲರೇಟ್ ಆಗ್ತಿದೆ ಅಂದ್ರೆ ಫೋರ್ಸ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ಮಾಸ್ ಇಂಟು ಆಕ್ಸಲರೇಷನ್. ಫೋರ್ಸು ಮತ್ತೆ ಅದರ ಆಕ್ಸಲರೇಷನ್ ಬರೀಬೇಕು ನಾವು. ಸೊ ಇಲ್ಲಿ ನೋಡಿ M2A ಅಂದ್ರೆ ಇದು ಕೆಳಗಡೆ ಹೋಗ್ತಾ ಇದೆ, ಇದು M2 ಇದೆ. ಸೊ M2A ಈಸ್ ಗೋಯಿಂಗ್ ಡೌನ್ ಡೈರೆಕ್ಷನ್. ಅದಕ್ಕೆ ಈಕ್ವಲೆಂಟ್ ಆಗಿರೋದು ಯಾವ್ದಪ್ಪ ಅಂದ್ರೆ M2G is also acting in the downward direction. ಯಾಕಂದ್ರೆ ಇದು this is acting in the downward direction. M2G is acting in the downward direction. This minus T, where T is a tension. See, ನಾವು ಪ್ರೀವಿಯಸ್ ಅಲ್ಲಿ ಫ್ರೀ ಬಾಡಿ ಡಯಾಗ್ರಾಮ್ ಅಂತ ಹೇಳಿದ್ವಿ. ಈ ಫ್ರೀ ಬಾಡಿ ಡಯಾಗ್ರಾಮ್ ಹೇಳ್ಬೇಕಾದ್ರೆ ಈ ನಾರ್ಮಲ್ ಅನ್ನೋದು ಒಂದು ಫೋರ್ಸು, ಟೆನ್ಷನ್ ಈಸ್ ಆಲ್ಸೋ ಎ ಫೋರ್ಸ್, ಫ್ರಿಕ್ಷನ್ ಈಸ್ ಆಲ್ಸೋ ಎ ಫೋರ್ಸ್. ಸೊ ಯು ಕ್ಯಾನ್ ರಿಮೆಂಬರ್ ದೀಸ್ ಥಿಂಗ್ಸ್ ವಿಲ್ ಬಿ we are going to use all this. This tension, ಈ ಟೆನ್ಷನ್ ಈ ಥ್ರೆಡ್ ಅಲ್ಲಿ ಇದೆ. This is acting in the opposite direction to this particular force. ಅದಕ್ಕೆ ಇಲ್ಲಿ ನಾವು ಇದನ್ನ -T ಅಂತ ಬರ್ಕೋತೀವಿ. ಇದನ್ನ ನೀವು ಈಕ್ವೇಷನ್ 1 ಅಂತ ತಗೊಳ್ಳಿ. ಅದೇ ತರ ದ ರಿಸಲ್ಟಿಂಗ್ ಅಪ್ವರ್ಡ್ ಫೋರ್ಸ್ ಇದ್ರದ್ದು ಯಾವ್ದ್ರದ್ದು M1, ಇದು ಕೆಳಗಡೆ ಹೋಗ್ಬೇಕು ಅಂದ್ರೆ ಇದು ಮೇಲ್ಗಡೆ ಹೋಗ್ಲೇಬೇಕಾಗುತ್ತೆ. ದಿಸ್ ಶುಡ್ ಆಕ್ಚುಲಿ ಮೂವ್ ಇನ್ ದಿ ಅಪ್ವರ್ಡ್ ಡೈರೆಕ್ಷನ್ ವಿತ್ ದಿ ಸೇಮ್ ಆಕ್ಸಲರೇಷನ್. ಸೊ M1A is equal to T ಮೈನಸ್, ನೋಡಿ ಇಲ್ಲಿ ಉಲ್ಟಾ ಇದೆ, T ಮೈನಸ್ M1G. ಇಲ್ಲಿ M1G ಕೆಳಗೆ ಹೋಗ್ತಿಲ್ಲ, ಮೇಲ್ಗಡೆ ಹೋಗ್ತಿದೆ, ಅಂಡ್ ದೇರ್ಫೋರ್ ಯು ರೈಟ್ ಇಟ್ ಆಸ್ ಎ ಮೈನಸ್ ಸೈನ್. ಇದನ್ನ ಈಕ್ವೇಷನ್ 2 ಅಂತ ಕರೀರಿ. ಇಲ್ಲಿ ನನಗೇನ್ ಬೇಕು, ಐ ವಾಂಟ್ ಟು ಫೈಂಡ್ ಔಟ್ ಆಕ್ಸಲರೇಷನ್. ಈ ಟೋಟಲ್ ಸಿಸ್ಟಮ್ದು ಆಕ್ಸಲರೇಷನ್ ಎಷ್ಟು ಅಂತ ಕಂಡುಹಿಡಿಬೇಕು. ಇವಾಗ ನಾವು ಪ್ರತಿ ಸಲಿನೂ ಈ ತರ ಫ್ರೀ ಬಾಡಿ ಡಯಾಗ್ರಾಮ್ ಬರೆದು ಈಕ್ವೇಷನ್ ಸಾಲ್ವ್ ಮಾಡಬೇಕಾದ್ರೆ ನಾವು ಮನ್ಸಲ್ಲಿ ಒಂದು ಇಟ್ಕೋಬೇಕು. ಏನ್ ಇಟ್ಕೋಬೇಕಪ್ಪ ಅಂದ್ರೆ, ನನಗೆ ಬೇಕಾಗಿರೋ ಟರ್ಮ್ ಬೇಕು, ಇಲ್ಲಿ ಎ ಬೇಕು ನನಗೆ, ಈ ಎ ಟರ್ಮ್ ಬೇಕು ಅಂದ್ರೆ ಯಾವ್ದನ್ನ ಎಲಿಮಿನೇಟ್ ಮಾಡ್ಬೋದು ನಾನಿಲ್ಲಿ ಅಂತ ನೋಡ್ಬೇಕು. ಇಲ್ಲಿ T2 ನೋಡಿ, ಎರಡರಲ್ಲೂ ಸ್ಕೇಮ್ ಇದೆ, ಅದನ್ನ ಎಲಿಮಿನೇಟ್ ಮಾಡ್ಬೋದು. ಇದೆರಡನ್ನು ಎಲಿಮಿನೇಟ್ ಮಾಡ್ಬೇಕಂದ್ರೆ ನಾನು ಈ ಈಕ್ವೇಷನ್ಗೆ ಏನ್ ಮಾಡಬೇಕು ಅಂತ ಪ್ರಶ್ನೆ ಕೇಳಿದ್ರೆ ನೀವು ನೋಡಿ, ನಾವು ಈಕ್ವೇಷನ್ 1 ಮತ್ತೆ 2 ನ ಆಡ್ ಮಾಡ್ತೀವಿ. ನೋಡಿ, ನೀವು ಆಡ್ ಮಾಡ್ತಿರೋ, ಮಲ್ಟಿಪ್ಲೈ ಮಾಡ್ತಿರೋ, ಸಬ್ಟ್ರಾಕ್ಟ್ ಮಾಡ್ತಿರೋ, ಡಿವೈಡ್ ಮಾಡ್ತಿರೋ, ಇಟ್ ಆಲ್ ಡಿಪೆಂಡ್ಸ್ ಆನ್ ನಿಮಗೆ ಏನು ಬೇಕು ಅನ್ನೋದ್ರ ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗುತ್ತೆ. ಅದರ ಬೇಸಿಸ್ ಮೇಲೆ ನೀವು ಈಕ್ವೇಷನ್ಸ್ನ ಆ್ಯಡ್ ಮಾಡೋದು ಸಬ್ಟ್ರಾಕ್ಟ್ ಮಾಡೋದು ಅದನ್ನು ನೋಡ್ಬೋದು. ನೀವು ಇದನ್ನು ನೀವು ಪ್ರಾಕ್ಟೀಸ್ ಮಾಡಿದ್ರೆ ಯು ವಿಲ್ ಬಿ ಏಬಲ್ ಟು ಸಾಲ್ವ್ ಪ್ರಾಬ್ಲಮ್ಸ್. ನಿಮಗೆ ಐಡಿಯಾ ಗೊತ್ತಾಗುತ್ತೆ ಯಾವಾಗ ಆ್ಯಡ್ ಮಾಡಬೇಕು ಯಾವಾಗ ಡಿವೈಡ್ ಮಾಡಬೇಕು ಅಂತ. ಸೊ ಇಲ್ಲಿ ನೋಡಿ 2 ಈಕ್ವೇಷನ್ ಇದೆ, ಇದೆರಡನ್ನು ಆ್ಯಡ್ ಮಾಡ್ತೀನಿ ನಾನು. ಆ್ಯಡ್ ಮಾಡಿದಾಗ ಏನು ಸಿಗುತ್ತೆ ನೋಡಿ, m1a ಪ್ಲಸ್ m2a, ಎರಡೂ ಕಡೆ ಲೆಫ್ಟ್ ಸೈಡಲ್ಲಿ m1a ಪ್ಲಸ್ m2a ತೊಗೊಂಡಿದ್ದೀನಿ ನಾನು. ದಟ್ ಈಸ್ ಈಕ್ವಲ್ ಟು m1a t ಮೈನಸ್ m1g ಪ್ಲಸ್ m2g ಮೈನಸ್ t. ನೋಡಿ ಇಲ್ಲಿ t ಮತ್ತು t ಕ್ಯಾನ್ಸಲ್ ಆಗುತ್ತೆ. ಇದಾದರೆ ಎರಡರಲ್ಲೂ g ಕಾಮನ್ ಇದೆ. ಸೊ ಯು ಕ್ಯಾನ್ ಟೇಕ್ m1 ಪ್ಲಸ್ m2. ಅಫ್ಕೋರ್ಸ್ ದೆರ್ ಇಸ್ ಎ ನೆಗೆಟಿವ್ ಸೈನ್ ಫಾರ್ ದಿಸ್ ಇಯರ್, ಅದನ್ನು ಆಮೇಲೆ ಶಿಫ್ಟ್ ಮಾಡೋಣ ಇಲ್ಲಿ. ಸೊ ಮಾಡಿದರೆ ನಿಮಗೆ ಆಕ್ಸಲರೇಷನ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ನೋಡಿ m2 ಮೈನಸ್ m1 ಡಿವೈಡೆಡ್ ಬೈ m1 ಪ್ಲಸ್ m2 ಅಂತ ಬರುತ್ತೆ. ಕ್ಲಿಯರ್ ಆಗಿ ಇಲ್ಲಿ ಏನು ಗೊತ್ತಾಗ್ತಿದೆ ನನಗೆ, ದಿಸ್ ಆಕ್ಸಲರೇಷನ್ ಈಸ್ ಲೆಸ್ ದೆನ್ ದಿ ಆಕ್ಸಲರೇಷನ್ ಡ್ಯೂ ಟು ಗ್ರಾವಿಟಿ ಅಂತ ಗೊತ್ತಾಗಿದೆ. ಸೊ ಅದೇ ಥರ ಯು ಕ್ಯಾನ್ ಆಲ್ಸೋ ಫೈಂಡ್ ಔಟ್ ವಾಟ್ ಈಸ್ ದಿ ಟೆನ್ಷನ್, ಇನ್ ದಿಸ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಸ್ಟ್ರಿಂಗ್. ಅದನ್ನು ನೋಡಬೇಕಾದ್ರೆ ನೀವು ಅದೇ ಸೇಮ್ ಈಕ್ವೇಷನ್ ಬರ್ದಿದ್ವಲ್ಲ ನಾವು, ಆ ಈಕ್ವೇಷನಲ್ಲಿ ಇಫ್ ಯು ಡಿವೈಡ್ ಈಕ್ವೇಷನ್ 1 ಬೈ ಈಕ್ವೇಷನ್ 2, ಅವಾಗ m2a ಡಿವೈಡೆಡ್ ಬೈ m1a is equal to m2g ಮೈನಸ್ ಟಿ ಡಿವೈಡೆಡ್ ಬೈ ಟಿ ಮೈನಸ್ m1g ತಗೊಂಡ್ರೆ ನಿಮ್ಗೆ ಇಲ್ಲಿ ನೋಡಿ ಎ ಕ್ಯಾನ್ಸಲ್ ಆಗುತ್ತೆ. ಸಾರಿ, m2 ಬೈ m1 ಆಯಿತು. ದಿಸ್ ಇಸ್ ಈಕ್ವಲ್ ಟು m2g ಮೈನಸ್ ಟಿ ಡಿವೈಡೆಡ್ ಬೈ ಟಿ ಮೈನಸ್ m1g. ಸಾಲ್ವ್ ಮಾಡಿ ಇದನ್ನು ಕ್ರಾಸ್ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡ್ಬೋದು. ಇಲ್ಲಿ ಮಾಡಿದ್ರೆ ಯು ವಿಲ್ ಗೆಟ್ ಟಿ ಇಸ್ ಈಕ್ವಲ್ ಟು 2m1 m2 ಡಿವೈಡೆಡ್ ಬೈ m1 ಪ್ಲಸ್ m2. ನೋಡಿ ಈ ಸಿಸ್ಟಮು 2 ಮಾಸ್ ಸಿಸ್ಟಮ್ಗೆ ತೊಗೊಂಡಿದ್ದೀವಿ. ಯು ಕ್ಯಾನ್ ಹ್ಯಾವ್ ಮೋರ್ ನಂಬರ್ ಆಫ್ ಇಲ್ಲಿ ಇನ್ನೊಂದು ಪುಲ್ಲಿ ಇರ್ಬೋದು, ಇನ್ನೊಂದು ಪುಲ್ಲಿ ಇದ್ದರೆ ಅವಾಗ ಇನ್ನೊಂದು ಅದರದ್ದು ಇಲ್ಲಿ 2 ಮಾಸ್ ಹಾಕ್ಬೋದು. ಅದು ಹೇಗೆ ಆಕ್ಸಲರೇಟ್ ಆಗುತ್ತೆ ಅಂತ ಮಾಡ್ಬೋದು. ಇದೆಲ್ಲ ಕೇಸಲ್ಲೂ ಆಲ್ ದಟ್ ಯು ನೀಡ್ ಟು ಡೂ ಇಸ್ ಪ್ರತಿಯೊಂದು ಬಾಡಿನೂ ಐಸೋಲೇಟ್ ಮಾಡಿ ಅದಕ್ಕೆ ಫ್ರೀ ಬಾಡಿ ಡಯಾಗ್ರಾಮ್ ಬರೀಬೇಕು. ಇವಾಗ m2 ಅಂತ ತೊಗೊಂಡ್ರೆ ಇಲ್ಲಿ ನೋಡಿ m2 ಅಂತಿದ್ರೆ ಇದರಲ್ಲಿ ಏನೇನು ಫೋರ್ಸ್ ಆ್ಯಕ್ಟ್ ಮಾಡ್ತಿದೆ ಅಂದರೆ m2g ಇನ್ ದಿ ಡೌನ್ವರ್ಡ್ ಡೈರೆಕ್ಷನ್. ಈ ಬಾಡಿ ಕೆಳಗಡೆ ಬರ್ತಿದೆ, ದೇರ್ ಫೋರ್ m2a. ಇಲ್ಲೊಂದು ಟೆನ್ಷನ್ ಇದೆ, ಆ ಟೆನ್ಷನ್ನ ಟಿ ಅಂತ ಬರ್ಕೋತೀರಿ. ಸೊ ಈ ಥರ ನೀವು ಈಕ್ವೇಷನ್ಸ್ ಬರ್ಕೊಂಡು ಹೋದರೆ ಇಟ್ ಈಸ್ ವೆರಿ ಈಸಿ ಫಾರ್ ಯು ಟು ಆ್ಯಕ್ಚುಲಿ ಸಾಲ್ವ್. ಸೊ ವಿ ಶಲ್ ಮೂವ್ ನೆಕ್ಸ್ಟ್. ನೋಡಿ ಇದೇ ಥರ ಕನೆಕ್ಟೆಡ್ ಬಾಡೀಸ್ ಇದ್ದರೆ ಇವಾಗ ವಾಟ್ ಈಸ್ ದ ಫೋರ್ಸ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್ಡ್ ಬೈ m2 ಇಯರ್ ಇನ್ ದಿಸ್ ಕೇಸ್ ಅಂತಂದರೆ, ಅಂದರೆ ಈ ಕಾಮನ್ ಇಂಟರ್ಫೇಸ್ ಏನಿದೆ m1 ಅಂಡ್ m2 ಮಧ್ಯದಲ್ಲಿ ಏನೊಂದು ಕಾಮನ್ ಇಂಟರ್ಫೇಸ್ ಇದೆ, ಈ ಇಂಟರ್ಫೇಸಲ್ಲಿ ಏನು ಫೋರ್ಸ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್ ಆಗ್ತಿದೆ ಅಂತ ಕೇಳಿದ್ರೆ ದಟ್ ಈಸ್ ದಿ ಫೋರ್ಸ್ ಆನ್ m2 ಅಂತ ಕೇಳಿದ್ರೆ ನೀವು ವಿ ನೋ ವೆರಿ ವೆಲ್ ದಟ್ ಫೋರ್ಸ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ಮಾಸ್ ಇಂಟು ಆಕ್ಸಲರೇಷನ್. ದೇರ್ ಫೋರ್ ಆಕ್ಸಲರೇಷನ್ ವಿಲ್ ಬಿ ದಿ ಫೋರ್ಸ್ ವಿಚ್ ಇಸ್ ಆಕ್ಚುಲಿ ಅಪ್ಲೈಡ್ ಇಯರ್ ಇಸ್ f, that divided by the total mass here is m1 plus m2. See, this is very similar to f is equal to ma and a is equal to force divided by mass. So ಈ acceleration is force divided by the net mass. ಇಲ್ಲಿ ಬರೀ m ತಗೊಂಡಿದ್ವಿ, ಇಲ್ಲಿ ಎರಡು ಮಾಸ್ ಇದೆ, ಇದು ಎರಡು ಕನೆಕ್ಟೆಡ್ ಆಗಿದೆ and therefore you should take m1 plus m2. ಸೊ ಹಿಂಗೆ ತಗೊಂಡ್ರೆ ಇಲ್ಲಿ ಒಂದು ಫೋರ್ಸ್ ಇದೆಯಲ್ಲ ವೇರ್ m1 is pushing this m2, ಆ f will be m2a. ಯಾಕೆಂದರೆ ವಿಚ್ ಇಸ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸಿಂಗ್ m2 is experiencing the acceleration because of the force there. We shall replace this a value in this. ಮಾಡಿದರೆ you will know that this would be m2f divided by m1 plus m2 ಅಂತಾಗುತ್ತೆ. and therefore if you want acceleration of the system, ಈ ಸಿಸ್ಟಮ್ ಹೆಂಗೆ ಆಕ್ಸಲರೇಟ್ ಮಾಡ್ತಿದೆ ಅಂತ ನೋಡಿದ್ರೆ ನೀವು a is equal to f divided by m1 plus m2 ಅಂತ ಮಾಡ್ಬೋದು. ಸೊ ಈ ಥರ ಯು ಕ್ಯಾನ್ ರೈಟ್ ಫ್ರೀ ಬಾಡಿ. ನೋಡಿ ಇಲ್ಲೂ ಅಷ್ಟೇ ನಾನು ಫ್ರೀ ಬಾಡಿ ಡಯಾಗ್ರಾಮ್ ಮಾಡಿರೋದ್ರಿಂದ ಆಯಿತು. ಇಲ್ಲಿ ಇನ್ನೊಂದು ವಿಚಾರ ಹೇಳಬೇಕಾಗುತ್ತೆ, ಇಲ್ಲಿ ಬಾಡಿ ಆಕ್ಸಲರೇಟಿಂಗ್ ಇನ್ ದಿಸ್ ಡೈರೆಕ್ಷನ್, ಈ ಡೈರೆಕ್ಷನಲ್ಲಿ ಏನು ಫೋರ್ಸೇ ಇಲ್ವಾ ಅಂದರೆ ಈ ಡೈರೆಕ್ಷನಲ್ಲಿ ಫೋರ್ಸ್ ಇದೆ. ನೋಡಿ ಇಲ್ಲಿ m1g ಇಸ್ ಆಕ್ಟಿಂಗ್ ಇನ್ ದ ಡೌನ್ವರ್ಡ್ ಡೈರೆಕ್ಷನ್, ಇದಕ್ಕೆ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಆಗಿರುವಂಥ ನಾರ್ಮಲ್ ಫೋರ್ಸ್ ಇಲ್ಲಿದೆ. ಅದೇ ಥರ ಇಲ್ಲಿ m2g ಇದೆ, ಇದಕ್ಕೆ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಇರೋ ನಾರ್ಮಲ್ ಫೋರ್ಸ್ ಇದೆ. ಇಯರ್ n is equal to m1g, ವಿಲ್ ಕಾಲ್ ಇಟ್ n1 and n2. ಸೊ n2 is equal to m2g ಆಗುತ್ತೆ. ಇದೆರಡೂ ಫೋರ್ಸ್ ಬ್ಯಾಲೆನ್ಸ್ ಆಗಿರೋದ್ರಿಂದ ದ ಬಾಡಿ ಇಸ್ ನಾಟ್ ಮೂವಿಂಗ್ ಇನ್ ದಿ ವರ್ಟಿಕಲ್ ಡೈರೆಕ್ಷನ್. ಈ ಡೈರೆಕ್ಷನಲ್ಲಿ ಮೂವ್ಮೆಂಟ್ ಇಲ್ಲ, ಈ ಡೈರೆಕ್ಷನಲ್ಲಿ ಮಾತ್ರ ಇದೆ. ಅದಕ್ಕೆ ಈ ಡೈರೆಕ್ಷನ್ ಇರುವಂಥ ಫೋರ್ಸನ್ನು ಮಾತ್ರ ನೀವು ಬರೆದ್ರೆ ಸಾಕು. ಇದಕ್ಕೆ ಮಾತ್ರ ಫೋರ್ಸ್ ಇಕ್ವೇಷನ್ ಎಲ್ಲ ಕಡೆನೂ f is equal to ma ಯೂಸ್ ಮಾಡಿ ಈ ಡೈರೆಕ್ಷನ್ ಇರೋ ಫೋರ್ಸ್ ಮಾತ್ರ ಮೆನ್ಷನ್ ಮಾಡಿದ್ರೆ ನೀವು ಯು ಕ್ಯಾನ್ ರೈಟ್ ಈಕ್ವೇಷನ್ಸ್ ಆಫ್ ಮೋಷನ್ ವೆರಿ ಈಸಿಲಿ. ಅಂದರೆ ಯು ಕ್ಯಾನ್ ಯೂಸ್ ದಿಸ್ ಈಕ್ವೇಷನ್ಸ್. ಸೊ ಸಿಮಿಲರ್ಲಿ ಇದ್ರದ್ದು ಅಷ್ಟೇ, ಇಲ್ಲೂ ಅಷ್ಟೇ ನೀವು ಯು ಕ್ಯಾನ್ ಆಕ್ಚುಲಿ ಸಿ ಇಲ್ಲಿ ಈ ಬಾಡಿ ಆಕ್ಸಿಲರೇಟ್ ಆಗ್ತಿದೆ, ಇಲ್ಲಿ ಇದು ಈ ಕಡೆ ಆಕ್ಸಿಲರೇಟ್ ಆಗಬೇಕು ಅಂದರೆ ಈ ಬಾಡಿ ಈ ಕಡೆ ಕೆಳಗಡೆ ಆಕ್ಸಿಲರೇಟ್ ಆಗಲೇಬೇಕು. ದೇರ್ ಇಸ್ ಅ ಪುಲ್ಲಿ ಸಿಸ್ಟಮ್ ಇಯರ್, ಥ್ರೆಡ್ ಈಸ್ ಗೋಯಿಂಗ್ ಓವರ್ ದೇರ್, ಇಲ್ಲಿ ಟೆನ್ಷನ್ ಇದೆ ಆ್ಯಕ್ಚುಲಿ. ಸೊ ಇಲ್ಲಿ ನೋಡಿದ್ರೆ ನೀವು ನೋಡಿ ಮಾಸ್ ಇಂಟು ಆಕ್ಸಿಲರೇಷನ್, ದಿ ಟೋಟಲ್ ಮಾಸ್ ಇದು ಎರಡರದು ಮಾಸ್ ಎರಡೂ ಮೂವ್ ಆಗ್ತಿರೋದು m1 ಪ್ಲಸ್ m2 ಇಂಟು ಎ ಇಸ್ ಈಕ್ವಲ್ ಟು, ಇದು ಆಕ್ಸಿಲರೇಟ್ ಆಗಬೇಕಂದ್ರೆ ಈ ಪೂರ್ತಿ ಸಿಸ್ಟಮ್ ಆಕ್ಸಿಲರೇಟ್ ಆಗಬೇಕಂದ್ರೆ m2g ಶುಡ್ ಆಕ್ಚುಲಿ ಗೋ ಡೌನ್, therefore this is m2g. ಅದನ್ನು ತಗೊಂಡ್ರೆ ಯು ವಿಲ್ ಸಿ ದಟ್ ಎ ವಿಲ್ ಬಿ m2 ಡಿವೈಡೆಡ್ ಬೈ m1 ಪ್ಲಸ್ m2 ಇಂಟು g ಅಂತ ಮಾಡ್ಬೋದು. ಅದೇ ಥರ ನೀವು ಟೆನ್ಷನ್ ನೋಡಬೇಕು ಅಂದರೆ ಟೆನ್ಷನ್ ಟಿ ಈಸ್ ಈಕ್ವಲ್ ಟು ಯಾವುದಾದ್ರೂ ಒಂದು ಸಿಸ್ಟಮ್ ತಗೊಳ್ಳೋಣ, ಟಿ ಈಸ್ ಈಕ್ವಲ್ ಟು m1a. ಈ ಕಡೆ ಟೆನ್ಷನ್ ಎಷ್ಟು ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್ ಮಾಡ್ತಿದೆ ಅಂದರೆ ದಟ್ ಈಸ್ ಆಕ್ಚುಲಿ ಈಕ್ವಲ್ ಟು ದಿ ಫೋರ್ಸ್ ವಿಚ್ ಇಸ್ ದರ್ ಹಿಯರ್. ಸೊ ಟಿ ಈಸ್ ಈಕ್ವಲ್ ಟು m1a. ನಮಗೆ ಮುಂಚೆ ಎ ಗೊತ್ತಿಲ್ಲ, ಯು ಕ್ಯಾನ್ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ದಿಸ್ ವ್ಯಾಲ್ಯೂ ಆಫ್ ಎ ಇನ್ ದಿಸ್ ಮಾಡಿದರೆ ನೋಡಿ ಇಲ್ಲಿ m1 ಇಂಟು m2g ಡಿವೈಡೆಡ್ ಬೈ m1 ಪ್ಲಸ್ m2 ಅಂತ ಆಗುತ್ತೆ. ಸೊ ದಿಸ್ ಇಸ್ ನಥಿಂಗ್ ಬಟ್ m1 m2g ಡಿವೈಡೆಡ್ ಬೈ m1 ಪ್ಲಸ್ m2 ಅಂತ ಮಾಡ್ಬೋದು. ಸೊ ಇಲ್ಲಿವರೆಗೂ ನಾವು ಫೋರ್ಸಸ್ ವಿಚ್ ಆರ್ ಆಕ್ಚುಲಿ ಪಾಸಿಟಿವ್ ಬಗ್ಗೆನೇ ಮಾತಾಡಿದೀವಿ. ಫೋರ್ಸಸ್ ಕೆನ್ ಆಲ್ಸೋ ಬಿ ನೆಗೆಟಿವ್. ಅದು ಎಲ್ಲಿ ಶುರು ಆಗುತ್ತೆ ಅಂದರೆ ಇವಾಗ ಲೆಟ್ ಅಸ್ ಸೇ ಯು ಹ್ಯಾವ್ ಎ ಬಾಡಿ ವಿಚ್ ಇಸ್ ಆಕ್ಚುಲಿ ಮೂವಿಂಗ್. ಸಿ ಅಕಾರ್ಡಿಂಗ್ ಟು ನ್ಯೂಟನ್ಸ್ ಲಾಸ್ ಆಫ್ ಮೋಷನ್, ಅಕಾರ್ಡಿಂಗ್ ಟು ದ ಲಾ ಆಫ್ ಇನರ್ಷಿಯಾ, if a body is moving in a forward direction, what would actually happen is that it should actually continue to move, because we know that according to the Newton's first law of motion, which is the law of inertia, which tells about the definition of the force, ಅಂದ್ರೆ ಫೋರ್ಸ್ ಅನ್ನೋದಿದೆ ಅಂತ ನಮ್ಗೆ ಅಲ್ಲೇ ಗೊತ್ತಾಗೋದು. ಸೊ ನೋಡಿ ಫೋರ್ಸ್ ಇದೆ, ಹಾಗಾಗಿ ಬಾಡಿ ಆಕ್ಸಿಲರೇಟ್ ಆಗ್ತಿದೆ. ಫೋರ್ಸ್ ಇದೆ, ಆಕ್ಸಿಲರೇಟ್ ಆಗ್ತಿದೆ ಅಂದರೆ ಅದು ಕಂಟಿನ್ಯೂಸ್ ಆಗಿರಬೇಕಾಗಿತ್ತು. ಆದರೆ ನಾನು ಯಾವುದೋ ಒಂದು ಬಾಲನ್ನು ನೆಲದ ಮೇಲೆ ಬಿಸಾಕಿದ್ರೆ ಒಂದು ಸ್ವಲ್ಪ ದೂರ ಆ ಬಾಲ್ ಓದ್ ಬಂದರೆ ಇಟ್ ವಿಲ್ ಆಕ್ಚುಲಿ ಸ್ಟಾಪ್. ಇದು ಸ್ಟಾಪ್ ಆಗಬೇಕು ಅಂದರೆ ಇದಕ್ಕೊಂದು ಫೋರ್ಸು ಇನ್ ದ ಆಪೋಸಿಟ್ ಡೈರೆಕ್ಷನ್ ಆಕ್ಟ್ ಮಾಡ್ತಾ ಇರ್ಬೋದು. ಇದು ಎಲ್ಲಿದೆಯಪ್ಪ ಫೋರ್ಸು ಅಂದರೆ ದಿಸ್ ಇಸ್ ದ ಫ್ರಿಕ್ಷನ್ ಬಿಟ್ವೀನ್ ದಿ ಬಾಲ್ ಅಂಡ್ ದಿಸ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಫ್ಲೋರ್ ಇಯರ್. ಸೊ ಅದನ್ನೇ ನೋಡಿ ಆ ಫೋರ್ಸನ್ನೇ ನಾವು ಫ್ರಿಕ್ಷನ್ ಅಂತ ಕರಿತೀವಿ. ಸೊ ಫ್ರಿಕ್ಷನ್ ಇಸ್ ಬೇಸಿಕಲಿ ಎ ನೆಗೆಟಿವ್ ಫೋರ್ಸ್ ವಿಚ್ ಇಸ್ ಇಂಟ್ರೊಡ್ಯೂಸ್ಡ್ ಆಸ್ ಎ ನೆಗೆಟಿವ್ ಫೋರ್ಸ್ ಇಯರ್. ಸೊ ನಾನು ಫ್ರಿಕ್ಷನ್ ಇಲ್ಲ ಅಂದರೆ ನೋಡಿ, ಫ್ರಿಕ್ಷನ್ ನಮ್ಮ ಜೀವನದಲ್ಲಿ ತುಂಬ ಮುಖ್ಯ. ಫ್ರಿಕ್ಷನ್ ಇಲ್ಲ ಅಂದರೆ ನಾನು ಪೆನ್ ಇಟ್ಕೊಂಡು ಬರೆಯೋಕ್ಕೆ ಕೂಡ ಆಗಲ್ಲ, ನಡೆಯೋಕ್ಕೆ ಕೂಡ ಆಗಲ್ಲ. ಸೊ ಫ್ರಿಕ್ಷನ್ ಈಸ್ ಆಕ್ಚುಲಿ ಟು ಸೇ ಈಸ್ ಎ ಗುಡ್ ಇವಿಲ್, ಟು ಪುಟ್ ಇಟ್ ಇನ್ jovial words. So whenever a body moves or tends to move over the surface of another body, a force comes into play which acts parallel to the surface of the contact and opposes the relative motion. This opposing force is called friction. ಇಲ್ಲಿ ನೋಡಿ ಈ ಬಾಡಿ ಇಲ್ಲಿದೆ, ಇಲ್ಲೊಂದು ಫ್ರಿಕ್ಷನಲ್ ಫೋರ್ಸ್ ಬರುತ್ತೆ. ಇವಾಗ ಇದು ಫ್ರಿಕ್ಷನಲ್ ಫೋರ್ಸ್ ಇನ್ಕ್ರೀಸ್ ಆಗ್ತಾ ಇರುತ್ತೆ. ಯಾವುದೋ ಒಂದು ಸಂದರ್ಭದಲ್ಲಿ ಇದೆರಡೂ ಬ್ಯಾಲೆನ್ಸ್ ಆಗುತ್ತೆ. ಅವಾಗ ದ ಬಾಡಿ ವಿಲ್ ಆಕ್ಚುಲಿ ಕಮ್ ಅಂಡ್ ಸ್ಟಾಪ್ ಇಯರ್ ಅಂಡ್ ಇಟ್ ವಿಲ್ ನೋ ಮೋರ್ ಮೂವ್. ನೋಡಿ ದ ಬಾಡಿ ವಿಲ್ ನಾಟ್ ಮೂವ್ ಇನ್ ದಿ ವರ್ಟಿಕಲ್ ಡೈರೆಕ್ಷನ್. ಇಲ್ಲಿ ಇದು ಇಲ್ಲಿ ನೋಡಿ, ಇಲ್ಲಿ ಈ mg ಹೀಗಿದೆ, ಇದನ್ನ ನಾನು ರಿಸಾಲ್ವ್ ಮಾಡಿದ್ದೀನಿ mg sin θ ಮತ್ತೆ cos θ ಅಂತ. ಇಲ್ಲಿ ನೋಡಿ ಇಟ್ ಇಸ್ ಆಕ್ಚುಲಿ ಕಮಿಂಗ್ ಟು ಸ್ಟಾಪ್ ದೇರ್. ಸೊ ಫ್ರಿಕ್ಷನಲ್ ಫೋರ್ಸಸ್ ಅಲ್ಲಿ ಇಟ್ ಇಸ್ ಆಲ್ಸೋ ವೆರಿ ಇಂಪಾರ್ಟೆಂಟ್ ಟು ನೋ how the normal force is basically acting there. So ಇಲ್ಲಿ ನೋಡಿ, ಇಲ್ಲಿ this weight is actually acting in the downward direction. To this the normal force is actually here. ಅವಾಗ the body is actually at rest. So there is no force acting in the horizontal direction. ಇಲ್ಲೋ I am not pushing it or pulling it, and therefore the body will not move in this direction. Will it move in the vertical direction andre the weight mg is acting in a downward direction. There is a normal force here. The body will not move in either these particular directions. So no applied force, box is actually at rest. So now let us say we will slightly move here. Normal force ಈ ಕಡೆ ಶಿಫ್ಟ್ ಆಗಿದೆ ಅಂದರೆ you are trying to apply some force or you are trying to lift this here ಆ ಥರ ಏನೋ. ಹಂಗೆ ನೋಡಿದರೆ ನೋಡಿ ಇಲ್ಲೊಂದು ಟೆನ್ಷನ್ ಇದೆ. ಸೊ ಟಿಲ್ ಟೆನ್ಷನ್ ಬಂದ ತಕ್ಷಣ there is a frictional force which actually comes into play. So weak applied force, box still remains at rest, and the frictional force which is actually there here, mu s and n. What is this mu s? This is the coefficient of friction. What is this coefficient of friction? This coefficient of friction is force divided by the force of friction divided by the normal force. So ನೋಡಿ ಇಲ್ಲಿ now the normal force is actually shifted here. ಇಲ್ಲಿ push ಮಾಡ್ತಾ ಇದ್ದೀನಿ ಬಾಡಿನ. So frictional force increase ಆಗುತ್ತೆ. ಇಲ್ಲಿ increase ಆದರೆ the static friction force is equal to mu naught n, where n is the normal force. The body will start sliding now. So what is static friction andre the force of friction which comes into play between two bodies before one body actually starts moving. Nodi illi body move agalla over the other. Andre it will have a tendency to move, but it will not actually move. So static friction is basically a self-adjusting force. So coming to limiting friction, the maximum force of static friction which comes into play when a body starts moving. So idikke sliding friction the next stage idu yavado limiting friction over the surface of another body is called limiting friction, which will just start moving. So when it moves, then you actually have kinetic friction. The force of friction which comes into play when a body is in a steady motion over the surface of another body is called kinetic or dynamic friction. Dynamic yakandre move agtide anta artha. So this is denoted by Fk. So kinetic friction is less than the limiting friction actually. So idishtunu navu helodadre, let us say you have a box which begins to move when the applied force equals maximum static friction. Avaga nodi illi you can actually see, you can observe this particular green arrow here. As the applied force increases, static friction forces increases to keep the box at rest. It is not making it move, rather it is actually trying to keep the body at rest. Increase aito, illi tanka the body is actually at rest. Ivaga sudden agi enagutte, limiting frictional force, lastly it will lose. Therefore this area that you can actually see where the body is actually moving. Once the box is in motion, static friction is replaced by weaker kinetic friction. As I told you earlier, kinetic friction is less than the limiting friction. So there is a relative motion of the body here. So based on all this whatever we discussed, there are certain laws which are formulated to explain the law limiting friction. The force of limiting friction depends upon nature of the two surfaces in contact and their state of roughness. Adu ಎಷ್ಟು rough irutte adra mele depend agade. If it is more rough, then the frictional forces are greater. The force of limiting friction acts tangential to the two surfaces. Nodi previously notidri navu, if the force is actually acting in this direction, the frictional force will be between this body. Andre ee surface gu ee body gu madhye illi tangential agirutte, which is denoted by Fs, Fk or whatever it is. The force of limiting friction acts tangential to the two surfaces in contact and in the direction opposite to that of the applied force. So the force of limiting friction between any two surfaces is independent of the shape of the area of the surface in contact. So it is independent of whatever might be the shape, it doesn't depend actually on that. As long as the normal reaction remains the same, normal reaction force onde irbeku. The force of limiting friction between two given surfaces is directly proportional to normal reaction between the two surfaces, that is F is proportional to R, F is equal to mu s R, where constant of proportional to mu s is called coefficient of limiting friction. So circular motion of the car on a level road. Nodi, when the car is moving on the road, there is a wear and tear with respect to this tire and this particular road. So idaradunu itkondo, the friction is helping the car to actually move, but when it is taking a circular path, avaga the maximum speed with which the car can actually take a turn is given by V max is equal to square root of mu r into g. Idu henge andre illi nodi frictional force mu into mg ide. This is greater than or equal to the necessary centripetal force for this. So centripetal force is mv square divided by r. So v square elli mu cancel agutte. V square divided by rg is less than or equal to mu, and therefore V square is actually less than or equal to mu rg. Take the square root there, then you will have V is equal to square root of r times g. So when the car negotiates a curved level road, the force of friction between the road and the tire provides the necessary centripetal force. This is the idea behind this. So ivaga ಏನು ಮಾಡಬೇಕು, ಇದು ಕಂಟಿನ್ಯೂ ಆದರೆ ಅಂದರೆ ಪ್ರೀವಿಯಸ್ ಸ್ಟೇಟ್ ಕಂಟಿನ್ಯೂ ಆದರೆ ಏನಾಗುತ್ತೆ, the tire will always be experiencing this frictional force in this direction here and a frictional force here, because of which the tire would actually damage, and very soon you might have to actually replace the tires. To avoid that, we actually have what is called as a banking of road. ಅಂದರೆ ರೋಡನ್ನು ಸ್ವಲ್ಪ ಈ ಕಡೆ ರೈಸ್ ಮಾಡಿದ್ರೆ that angle here will actually give us the necessary centripetal force to negotiate that particular curve. So the system of raising the outer edge, the outer edge of the curved rod above its inner edge is called banking of the curved rod. So the velocity of the body in this particular case is actually given by V is equal to square root of mu plus tan theta divided by 1 minus mu tan theta, where you know what is mu here, which is coefficient of friction. So now this is what we had to actually talk about in terms of laws of motion. Now we will actually straight away come to work, power and energy. So now we shall actually see some synopsis of this work, power, energy. See, work is said to be done when a force acts on a body and the body moves through some distance in the direction of the force. And here force is a vector quantity, displacement of the body will be a vector quantity, but the work done is basically a scalar quantity. This work done is force into displacement into cos of the angle between them. So this work done is, as I told you, is a scalar quantity, and this can be positive, negative or 0 depending upon theta, the angle, whether it is acute or obtuse. The work done by friction or viscous force on moving bodies is basically negative, which we had discussed earlier when we talked about friction. If theta is equal to, notice this should actually be 0 degree, and this should be 90 degree. So here in this particular case you will actually see that the force is equal to work done is force into displacement. The work done will be maximum when the angle between this is equal to 0. So maximum force is actually applied in the direction of the displacement, and therefore maximum work is actually done. And if the angle is actually 90 degree, let us say this theta is equal to 90 degree, now you will see that the work done is equal to 0. Why? Because cos 90 is 0, and therefore the work done will be 0 in this case. So this work done can also be against the variable force. In the previous cases we talked about constant force is applied. Let us say you have a variable force applied. The work done by variable force of changing the displacement. So let us say it is starting from S1 to S2. In these we can actually divide this particular curve into smaller intervals, and then say each interval is basically a small ds, and then work done will be integral S1 to S2, that is from the initial distance to the final distance f dot ds, which is nothing but the area under the force displacement curve. So units of work, the SI unit of work is joule. 1 joule is 1 Newton into meter. So in CGS units it's dyne centimeter. 1 joule is basically 10 power 7 erg. So work done can also be represented in terms of rectangular components. So let us say you have a force which is actually acting in a 3-dimensional coordinate axis, in a coordinate axis basically. So let us say you have x, y and z axis, and this is the x component, this is the y component, this is j component. Similarly, the displacement which has actually occurred because of this force would also be in the x, y and z component, and therefore the work done in all these 3 cases will be f dot ds or f into s. So coming to energy, it is defined as the ability of the body to do work. So previously we have discussed about work, and energy is the ability to do work. It is measured by the amount of work that the body can actually do. It is basically a scalar quantity. Energy is basically a number, and therefore it is a scalar quantity. The SI unit of energy is joule. So the energy can also be represented in other forms here. 1 electron volt is 1.6 into 10 power minus 16 joule, and 1 kilo electron volt is 10 power 3 electron volt, and 1 mega electron volt is 10 power 3 electron volt, and so on. So this energy can be manifested in different kinds of bodies in 2 different ways. Kinetic energy anta irutte, potential energy anta irutte. Kinetic energy andre it is an energy possessed by the body by the virtue of its motion. Andre motion agodrinda, andre the body is actually moving, adu move agodrinda baruvanta energy irutte, that is kinetic energy. The kinetic energy of the body of mass m moving with speed v is k is equal to half mv square. You'll note mv is actually the momentum, p is equal to m into v, momentum. We had discussed in the previous synopsis. So you, to get this particular thing, you multiply this to m here, and therefore you will have p square divided by 2m. This can be represented in this particular way also. So this is very important, the work energy theorem. See, the work done by the net force acting on a body is equal to change in kinetic energy of the body. See, when the body is actually moving, let us say we can use the equations of motion, which is v square minus u square is equal to 2as, or v square is equal to u square plus 2as. Now, to get the kinetic energy form, let us multiply this equation by half m. Now, half m multiply madre, half m v square minus half m u square is equal to half m 2as agate. 2 cancel agate. Idu final kinetic energy aito. This is initial kinetic energy, which is equal to m a into s. But I know m a is force and s is the displacement. What is force into displacement? It is basically work done. Therefore, the work done can be written in terms of change in kinetic energy. ಈ ವರ್ಕ್ ಡನ್ ಅನ್ನ ಚೇಂಜ್ ಇನ್ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿಲಿ ಬರೆಯೋದನ್ನ ನಾವು ವರ್ಕ್ ಎನರ್ಜಿ ಥಿಯರಮ್ ಅಂತ ಕರಿತೀವಿ. ಸೊ ಇಟ್ಸ್ ಅ ವೆರಿ ಸಿಂಪಲ್ ಡಿರೈವೇಶನ್. The work energy theorem can be regarded as a scalar form of Newton's second law of motion. See, Newton's second law of motion alli, we know that force is nothing but rate of change of momentum, dp divided by dt, where dp is m into v minus u divided by t. So, hagagi this particular work energy theorem is actually a scalar form of Newton's second law. Coming to potential energy, as I told you earlier, energy is in the form of potential energy and kinetic energy. So, it is energy possessed by the body by virtue of its position in the field, andre gravitational field irutte. Ivaga arthide, illello ಒಂದು ಆಬ್ಜೆಕ್ಟ್ ಕೆಳಗಡೆ ಬೀಳ್ತಿದೆ ಅಂದ್ರೆ this particular object is in the gravitational field. ಆ field ಏನು g. ಈ gravitational field ಅಲ್ಲಿ ಬೀಳ್ತಿದೆ and therefore it is ಇಲ್ಲಿಂದ ಮೇಲ್ ತಗೊಂಡು ಹೋಗಿದ್ದೀವಿ. ಸೊ ಇಟ್ ಹಸ್ ಗೈನ್ಡ್ ಈ ಹೆಚ್ಚು ಡಿಸ್ಟೆನ್ಸ್ ಮೇಲ್ಗಡೆ ತಗೊಂಡು ಹೋಗಿರೋದ್ರಿಂದ ಇಟ್ ಡಸ್ ಪರ್ಟಿಕ್ಯುಲರ್ ವರ್ಕ್ ಡನ್ ಇನ್ ಟೇಕಿಂಗ್ ದಿಸ್ ಅಗೇನ್ಸ್ಟ್ ದಿಸ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಫೀಲ್ಡ್ has actually brought in some kind of a potential in this particular system, and this is the potential energy. Or the configuration of shape and size. Andre you can actually have a rubber ball which is actually squeezed. So when you are squeezing it, you are disturbing the molecules and bringing all the molecules closer, and therefore you can actually have energy stored in this. Bit takshana it will actually come out, pop out. So rubber ball irbodu, you would have actually seen all this. For a conservative force in one dimension, the potential energy functions. So idanna ee tar function allu baribodu. This force is du x divided by dx. So final potential energy minus initial energy potential energy is a change in energy. This change in energy is force into this distance. So I was discussing about gravitational potential energy. So you have an object here. So your mg is actually acting in the downward direction in the position A. Now I am going to place this in position B, and in doing so I have actually pushed this certain distance h, and therefore the potential energy stored will be mgh. Mg because this is the mass which is actually taken against the field to a certain height h, and therefore this potential energy is mgh. So it is energy possessed by the body by virtue of its position above the surface of the earth. The gravitational potential energy of the body of mass m at a height h above the earth's surface is u is equal to mgh. u ಅನ್ನೇ ನಾವು potential energy ಅಂತ ಕರಿತೀವಿ. So potential energy in a spring, ನೋಡಿ ಸ್ಪ್ರಿಂಗ್ ಅಲ್ಲಿ ಈ ಸ್ಪ್ರಿಂಗ್ ಸಿಸ್ಟಮ್ ಏನಿದೆ ಇದರಲ್ಲಿ ಎನರ್ಜಿ ವಿಲ್ ಆಕ್ಚುಲಿ ಬಿ ಸ್ಟೋರ್ಡ್. ಇವಾಗ ನಾನು ಫೋರ್ಸ್ ಅನ್ನ ಈ ಕಡೆ ಅಪ್ಲೈ ಮಾಡಿದ್ರೆ ಐ ಹ್ಯಾವ್ ಎಕ್ಸ್ಟೆಂಡೆಡ್ ದಿಸ್. ಇವಾಗ ಫಸ್ಟ್ ಇದನ್ನ ಪುಷ್ ಮಾಡ್ತೀನಿ ಒಳಗಡೆಗೆ, ಪುಷ್ ಮಾಡಿದ್ರೆ ಇಲ್ಲಿ ಬರುತ್ತೆ. ಪುಷ್ ಮಾಡಿದ್ರಿಂದ ಇದರಲ್ಲಿ ಏನಾಯ್ತು, ಐ ಹ್ಯಾವ್ ಸ್ಟೋರ್ಡ್ ಸಮ್ ಅಮೌಂಟ್ ಆಫ್ ಎನರ್ಜಿ ಇನ್ ದಿಸ್. ಬಿಟ್ಟಿದ ತಕ್ಷಣ ಇಟ್ ವಿಲ್ ಆಕ್ಚುಲಿ ಕಮ್ ಬ್ಯಾಕ್ ಇನ್ ದಿಸ್ ಡೈರೆಕ್ಷನ್. So you can actually store energy in this particular spring system. So potential energy of the spring, adralli according to Hooke's law, when a spring is stretched through a certain distance x, the restoring force set up in the spring due to its elasticity is such that, ನೋಡಿ ಅಲ್ಲಿ ನಾನು ಹೇಳಿದ್ದೆ potential energy is due to configuration ಅಂತ. This configuration ಅಂದ್ರೆ ಈ elasticity is basically telling you that it is basically because of the configuration. So F is proportional to the displacement. F is equal to minus k into x, where k is the constant. Here in this case it is a spring constant. It is a restoring force set up in the spring per unit extension. So its unit is Newton per meter. The work done in stretching the spring through distance x will be W is equal to, so I am stretching it from initial position 0 to some position x. So kx dx, which is half kx square. So which is nothing but the kinetic energy here. So this particular concept of force in this particular configuration, when we are talking about configuration, there are two types here, conservative and non-conservative. a force is conservative. When do you say that? If the work done by the force is displacing a particle from one point to another is independent of the path followed. See, let us say you are taking an object, ಒಂದು ಆಬ್ಜೆಕ್ಟ್ ಇದೆ, ಅದನ್ನು ಇನ್ಕ್ಲೈನ್ ಪ್ಲೇನಲ್ಲಿ ಕೆಳಗಡೆಯಿಂದ ಮೇಲ್ಗಡೆ ತಗೊಂಡು ಹೋಗ್ತಾ ಇದೀವಿ. ಎಷ್ಟು ದೂರ ತಗೊಂಡು ಹೋಗಿದ್ದೀವಿ ಅಂದರೆ mgh ಅಷ್ಟು ಡಿಸ್ಟೆನ್ಸ್, ಅಷ್ಟು h is a distance here, mg ಇದ್ರದ್ದು ಮಾಸು m ಇದೆ, so it is acted upon by gravity, acceleration due to gravity, and therefore mg is there. So I am taking this, I am displacing this particular body in this particular direction. So in the process I have actually done some work. So ಇದೇ ಥರ ಇವಾಗ ಅದರ ಬದಲು ನಾನು ಮೆಟ್ಲಿದೆ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ, ಬಟ್ ಈ ಡಿಸ್ಟೆನ್ಸ್ ಏನಿದೆ ಇದು ಸೇಮ್ ಇದು, ಅಂದರೆ ಈ ಎಚ್ ಏನಿದೆ ದಿಸ್ ಇಸ್ ಆ್ಯಕ್ಚುಲಿ ಸೇಮ್, ಇಲ್ಲೇನಿದೆ ಇಲ್ಲೂ ಅದೇ ಅಂದರೆ ನೀನು ಮೆಟ್ಲು ಹತ್ಕೊಂಡು ಹಿಂಗೆ ಹೋದ್ರೂ ದಿ ವರ್ಕ್ ಡನ್ ಈಸ್ ಒನ್ಸ್ ಅಗೇನ್ ದಿ ಸ್ಟೋರ್ಡ್ ಪೊಟೆನ್ಷಿಯಲ್ ಎನರ್ಜಿ ಬೇಸಿಕಲಿ mgh only. So it is independent of the path. ಅವಾಗ ಅದನ್ನು ಕನ್ಸರ್ವೇಟಿವ್ ಫೋರ್ಸ್ ಅಂತ ಕರಿತೀವಿ. If the work done by the force in moving a particle around any closed path is zero. So some of the examples of conservative forces: gravitational force, electrostatic force, elastic force of the spring, and these are all conservative forces. So coming to non-conservative forces, if the amount of work done in moving an object against a force from one point to another depends on path along which the body moves, then such a force is actually called a non-conservative force. Example: forces of friction and viscosity. ಇವಾಗ ಯಾವುದೋ ಒಂದು ಎಲೆ ಕೆಳಗಡೆ ಬೀಳ್ತಿದೆ ಅಂದರೆ, ಸೊ mg is acting in the downward direction, ಒಂದು ಲೀಫ್ ಇದೆ ಆಯಿತಾ, ಸೊ ಯು ಹ್ಯಾವ್ mg acting in the downward direction, but at the same time you have the atmospheric air which is actually in this particular direction, which is disturbing. The net force acting on this will actually different, and therefore it would actually move in this particular fashion, and therefore this is basically non-conservative. So the work done will be different. If I'm taking it here, the work done is different than when it is actually randomly moving in this particular way. So this is basically a non-conservative force. So according to mass energy equivalence, mass can be converted into energy and energy can be converted into mass. So we have this equation E is equal to mc square, so which would actually dealt with this in the second year part more. So some of the examples of that is annihilation of the matter. When an electron and a positron annihilate, ಅಂದರೆ ಅದೆರಡು ಮರ್ಜ್ ಆದಾಗ, so each other forming two gamma rays. So ಅಂದರೆ the mass is getting converted into energy, where this gamma rays is basically electromagnetic radiation. So energy generation in sun, stars due to conversion of mass into energy. So coming to power, it is a rate of doing work. So it is a scalar quantity. Power is work divided by time. So these are some of the units of work. 1 watt is 1 joule per second. 1 kilowatt is 1000 watt. We also use this. 1 horsepower is 746 watt. In all the household equipments, we actually have this convention of using horsepower. So law of conservation of energy, it states that energy can neither be created nor be destroyed, but can only be transferred from one form to another. So this is a very important consequence of learning science. So illi, if somebody says that something can actually be created out of nothing, so you can actually challenge and say that it should not be violating the law of conservation of energy. So this is a very powerful tool in analyzing the science of everyday life. The total energy of an isolated system remains a constant. So coming to collisions, a collision between two bodies is said to occur if either physically collide each other or the path of the motion of one body is influenced by the other. Suppose let us say you have a magnet and then you have another magnet which is actually having the same poles. When I bring closer to this, even without actually touching, you will actually see that this will actually be deflected in a particular direction. So idli enagtide andre it is actually changing the path, but without actually touching each other. So you can have such kind of collisions also. So you have collisions are classified into elastic and inelastic collision. So elastic collision, if there is no loss in kinetic energy during the collision, it is called elastic collision. Andre before collision you have these two masses which are actually moving with certain velocities. So during collision the bodies will actually come in contact with each other. After collision, this body is going to move with certain velocity and this body is going to move with certain velocity. So when the bodies actually get separated after the collision, then such kind of collision is actually called elastic collisions. So coming to inelastic collision, if there is a loss in kinetic energy during the collision, it is an inelastic collision. So then what will actually happen is, before collision the bodies were actually intact, separate, but after collision the bodies will actually stick to each other. So that is basically inelastic collision. So perfectly inelastic collision is basically this, in inelastic collision in which two bodies stick together after the collision. So head-on collision, it's a collision in which the colliding bodies move along the same straight line path before and after the collision. So there is something called as an oblique collision also. If two bodies do not move along the same straight line path before and after the collision is said to be oblique. So you have this mass which is coming and hitting this particular mass with a certain angle, and this would move in this particular direction, this would move in this particular direction. Now you can actually see that this theta 1 is actually taken here. You can also find out what is the horizontal component of this velocity here and what is the vertical component of this velocity here. So these kind of situations are basically oblique collision. So a coefficient of restitution for a collision between two bodies is the ratio of magnitude of their relative velocity after collision to the magnitude of their relative velocity before the collision. So coefficient of restitution is actually equal to V1 minus V2 divided by U1 minus E2. So the coefficient of restitution can be used to distinguish between different types of collisions. So we discussed about elastic, inelastic, perfect elastic and all that. So based on that we can actually see for a perfectly elastic collision the coefficient of restitution is equal to 1. That is, relative velocity of separation is equal to relative velocity of approach. For an inelastic collision it lies between 0 and 1, that is, the relative velocity of separation is less than relative velocity of the approach. For a perfectly inelastic collision E is equal to 0, that is, relative velocity of separation is 0, the two bodies move together with a common velocity. For a super elastic collision E is greater than 1, the kinetic energy in this case actually increases. So now with all this synopsis we shall actually start with some few problems. So first we shall actually do some problems related to the laws of motion. So coming to the first problem, a stone of mass 0.1 kg is thrown vertically upwards. So ingida stone it is thrown vertically upwards. The direction and magnitude of the net force on the stone throughout its journey is anta keliyare. So 4 option ide, 0.98 Newton downwards, 0.98 Newton upwards, 0.98 Newton upwards while stone moves vertically downwards, 0.98 Newton downwards while the stone moves vertically downwards, and 0.98 Newton upwards while the stone moves vertically downwards, 0.98 Newton downwards when the stone moves downwards, and 0 at the highest point anta ide. So ಇಲ್ಲಿ ನೋಡಿದ್ರೆ the net force acting on the pebble anta bardi andre stone, nothing but stone is vertically downwards and it is equal to mg. So male ball ನಾವು ಈ stone ಅನ್ನು ಬಿಸಾಕಬೇಕಾದ್ರೆ mg is always acting in the downward direction, and therefore the mass into acceleration will be 0.98 Newton, and therefore it's always 0.98 in the downward direction. Therefore option A is the correct answer. Next problem, when the block moves horizontally, the normal reaction that is acting on the block as shown in the figure anta kelide. So illi free body diagram bariyodu tumba important agutte to solve this problem. So we have this mass which is actually a force is acting in a particular angle here. So and then you see here we can write the free body diagram here. This mass is there, ಇದನ್ನು resolve ಮಾಡಿದೀವಿ horizontal ಮತ್ತೆ vertical component ಆಗಿ. So you have f cos theta here and you have f sin theta here. So mg is acting in the downward direction. To this you have a normal force. These two forces are basically balanced, and therefore the body is not moving in the vertical direction here. So this normal force plus f sin theta is equal to m into g. So I want n, therefore it is mg minus f sin theta, and therefore option D is the correct answer here. So in a tug of war contest, two groups of people pull on horizontal rope from the two ends. The winning group will be one which anta. Tug of war andre hagga jagga aata, adu nivella ಆಡಿರ್ತೀರಾ. So exerts greater force on the rope, exerts a force on the rope which is greater than the tension in it, exert greater force on the ground, makes a greater angle with the horizontal ಇದೆ. ನೋಡಿ ಇವರು they are pushing each other. ಇಲ್ಲೊಂದು ಹಗ್ಗ ಇದೆ, so ಇವರು ಎಳಿತಿದ್ದಾರೆ ಇದನ್ನ. So ಇಲ್ಲಿ exerts greater force on the rope. So the tension here is all the same. So exerts on the force on the rope which is greater than the tension in it. ನೋಡಿ ಇಲ್ಲಿ ಇವರು ಎಷ್ಟು ಗ್ರೌಂಡ್ ಅನ್ನ ಕೆಳಗಡೆ ತಳ್ತಾ ಇದ್ದಾರೆ, ಇಲ್ಲಿ ಅವರು ಮಾಡಿರೋ ಆಕ್ಷನ್ ಗೆ ರಿಯಾಕ್ಷನ್ ಇದು, ಗ್ರೌಂಡ್ ರಿಯಾಕ್ಷನ್ ಇದೆ ಇಲ್ಲಿ, ದಿಸ್ ಅ ರಿಯಾಕ್ಷನ್. ಈ ರಿಯಾಕ್ಷನ್ ಇಸ್ ವಾಟ್ ಆಕ್ಚುಲಿ ಇಸ್ ವೆರಿ ಇಂಪಾರ್ಟೆಂಟ್ ಇನ್ ಸೀಯಿಂಗ್ ಹೂ ವಿಲ್ ಆಕ್ಚುಲಿ ವಿನ್ ಇನ್ ದಿಸ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಕಾಂಪಿಟೇಷನ್. ಹಂಗೆ ನೋಡಿದ್ರೆ So considering the two groups on the rope on a single system, it is easy to see that the only external forces acting on the system are frictional forces ಇದೆ. ಅವರು ಈ ಪುಲ್ ಮಾಡ್ತಿರೋರು ಮತ್ತೆ ಅವರ ಇದ್ರ ನಡುವೆ. ಸೊ ದಿ ನಾರ್ಮಲ್ ಫೋರ್ಸ್, ಗ್ರೇಟರ್ ದಿ ಫೋರ್ಸ್ ಯಾರು ಜಾಸ್ತಿ ಇದನ್ನು ಪುಷ್ ಮಾಡ್ತಾರೋ ಅವ್ರದ್ದು ನಾರ್ಮಲ್ ಫೋರ್ಸ್ ಆಟೋಮೆಟಿಕಲಿ ಜಾಸ್ತಿ ಆಗುತ್ತೆ ಇಲ್ಲಿ. ಸೊ ದೇರ್ ಫಾರ್ ಹೆನ್ಸ್ ದಿ ಸಿಸ್ಟಮ್ ವಿಲ್ ಮೂವ್ ಟುವರ್ಡ್ಸ್ ದಿ ಡೈರೆಕ್ಷನ್ ಆಫ್ ದಿ ಗ್ರೇಟರ್ ರಿಯಾಕ್ಷನ್. ಸೊ ಯಾರು ಜಾಸ್ತಿ ಭೂಮಿನ ಒತ್ತುತ್ತಾರೋ ಅವ್ರ ಕಡೆಗೆ ಯು ವಿಲ್ ಆಕ್ಚುಲಿ ಹ್ಯಾವ್ ದಿಸ್ rope and they will be the winners. So option C is the correct answer. So coming to the next problem. A rope hangs with one end tied over the branch of the tree. Its breaking strength is less than the weight of the person. So ಅವರೇನು ಹೇಳ್ತಿದ್ದಾರೆ, ಇವು ಒಂದು ಬ್ರಾಂಚ್ ಇದೆ, ಒಂದು ಮರದ ಪೊಟ್ರೆ ಇದೆ, ಇದಕ್ಕೆ ಒಂದು ಹಗ್ಗ ಹಾಕಿದ್ದೀವಿ, ಹೀಗಿದೆ, ಒಬ್ಬ ಮನುಷ್ಯ ಇದನ್ನು ಹಿಡ್ಕೊಂಡು ಮೇಲೆ ಹತ್ತೋ ಪ್ರಯತ್ನ ಮಾಡ್ತಿದ್ದಾನೆ. ಸೊ ದಿ ಎಮ್ ಜಿ ಈಸ್ ಆಕ್ಟಿಂಗ್ ಇನ್ ದಿ ಡೌನ್ವರ್ಡ್ ಡೈರೆಕ್ಷನ್ ಇಯರ್. ಸೊ ಇಲ್ಲಿ ಒಂದು ಟೆನ್ಷನ್ ಇದೆ ಇದರಲ್ಲಿ. ಸೊ ಅವ್ರೇನು ಹೇಳ್ತಿದ್ದಾರೆ ಅಂದರೆ ಇಟ್ಸ್ ಬ್ರೇಕಿಂಗ್ ಸ್ಟ್ರೆಂತ್ ಇಸ್ ಲೆಸ್ ದೆನ್ ದಿ ವೆಯ್ಟ್ ಆಫ್ ದಿ ಪರ್ಸನ್ ವಿತೌಟ್ ಗೆಟಿಂಗ್ ದ ರೋಪ್ ಬ್ರೇಕ್. ಆ ರೋಪ್ ಕಟ್ ಆಗಬಾರ್ದು ಅಂದರೆ, ಸ್ವಲ್ಪನೇ ಜಾಸ್ತಿ ಇದೆ, ಕಟ್ ಆಗಬಾರ್ದು ಅಂದರೆ ಆ ಮನುಷ್ಯ ಏನು ಮಾಡಬೇಕು ಅಂತ, ಅವನು ಹಾಗೆ ಹಿಡ್ಕೊಂಡಿದ್ರೆ ಹ್ಯಾಂಗ್ ಡೌನ್ ದಿ ರೋಪ್ ಫ್ರೀಲಿ, ಸ್ಲೈಡ್ ಡೌನ್ ದಿ ರೋಪ್ ವಿತ್ ಸಮ್ ಆಕ್ಸಿಲರೇಷನ್, ಹಿಡ್ಕೊಂಡು ಹಾಗೆ ವಿತ್ ಒಂದು ಸಮ್ ಆಕ್ಸಿಲರೇಷನ್ ಕೆಳಗಡೆ ಬರಬೇಕಾ, ಅವಾಗ ಕಟ್ ಆಗಲ್ವಾ? ಅಥವಾ ಹಿಡ್ಕೊಂಡು ಹತ್ತಾ ಇದ್ರೆ ಸ್ಲೈಡ್ ಅಪ್ ದಿ ರೋಪ್ ವಿತ್ ಕಾನ್ಸ್ಟೆಂಟ್ ವೆಲಾಸಿಟಿ, ಸ್ಲೈಡ್ ಡೌನ್ ದಿ ರೋಪ್ ವಿತ್ ಸಮ್ ಆಕ್ಸಲರೇಷನ್. ಇದರಲ್ಲಿ ಯಾವುದು ಕರೆಕ್ಟ್ ಆಪ್ಷನ್ ಅಂತ ನೋಡಿದ್ರೆ ಯು ವಿಲ್ ಆಕ್ಚುಲಿ ಸಿ, ಇದಕ್ಕೆ ಫ್ರೀ ಬಾಡಿ ಡಯಾಗ್ರಾಮ್ ಬರೆದ್ರೆ ಎಮ್ ಜಿ ಮೈನಸ್ ಟಿ ಇಸ್ ಈಕ್ವಲ್ ಟು ಎಮ್ ಇಂಟು ಎ, ಟಿ ಇಸ್ ಈಕ್ವಲ್ ಟು ಇದನ್ನ ಈ ಕಡೆ ಶಿಫ್ಟ್ ಮಾಡಿ ಎಮ್ ಜಿ ಮೈನಸ್ ಎಮ್ ಎ ಆಯಿತು, ಟಿ ಇಸ್ ಲೆಸ್ ದೆನ್ ಎಮ್ ಜಿ. ನೋಡಿ ಜಾಸ್ತಿ ಆಗಿದ್ದರೆ ಏನಾಗ್ತಿತ್ತು ಇಲ್ಲಿ, ಇಟ್ ವುಡ್ ಹ್ಯಾವ್ ಬೀನ್ ಸಮ್ ನಂಬರ್. ಸೊ ಜಾಸ್ತಿ ಆಗಬಾರ್ದು ಅಂದರೆ ಅವಾಗ ಕಟ್ ಆಗುತ್ತೆ ಅಂತ ಅರ್ಥ. ದೇರ್ ಫಾರ್ ದಿ ಪರ್ಸನ್ ಸ್ಲೈಡ್ಸ್ ಡೌನ್ ವಿತ್ ಸಮ್ ಆಕ್ಸಲರೇಷನ್, ಹಿಡ್ಕೊಂಡು ಮೇಲತ್ತೋ ಪ್ರಯತ್ನ ಮಾಡಬಾರ್ದು. ಬಟ್ ಇಫ್ ಯು ಜಸ್ಟ್ ಕಮ್ ಡೌನ್, only then the tension in the rope can be reduced to a value below the breaking rod which is less than the person's weight. So avaga it can actually be fine. So now we see that the option D is the correct option there. So coming to the next problem. A block of mass 5 kg rests on horizontal plane. Alli coefficient of friction kottidare, mu is equal to 5/12 anta. A force acting horizontally on the block is not able to displace it, then the contact force acting on the block would be, and the contact force ಕೇಳಿದ್ದಾರೆ. So ಇಲ್ಲಿ ನೋಡಿ, this is very interesting here. So when no external force is applied, the contact force acting on the block is 50 Newton. ಅದು ನಮಗೆ ಗೊತ್ತಿದೆ. So ಇಲ್ಲಿ if you actually see this force that we actually have here is basically 50 Newton ಇದೆ. ಸೊ ಇದಕ್ಕಿನ್ನ ಅದು ಆ್ಯಕ್ಚುಲಿ ಜಾಸ್ತಿ ಇರಬಾರ್ದು. ಇದಕ್ಕಿನ್ನ ಜಾಸ್ತಿ ಇಲ್ಲದೇ ಇರೋವಂಥ ಟೈಮಲ್ಲಿ ನಿಮಗೆ ಈ ಒಂದು ಸೆಕೆಂಡು, there is a problem there. See the question once again. A block of mass 5 kg rests on rough horizontal surface. A force acting horizontally on the block is not able to displace it. Then the contact force acting on the block could be ಅಂತ ಕೇಳಿದ್ದಾರೆ. ಸೊ ಇಲ್ಲಿ when the block, ಅಂದರೆ ಈ ಬ್ಲಾಕ್ when it is about to move or when it actually starts to move, then the contact force will be the force applied square plus the limiting force. ಸೊ ಇದ್ರದ್ದು ಸ್ಕ್ವೇರ್ ರೂಟ್ ತೊಗೊಂಡ್ರೆ ಐ ವಿಲ್ ಆ್ಯಕ್ಚುಲಿ ಹ್ಯಾವ್, ನೋಡಿ 50 ಸ್ಕ್ವೇರ್ ಇದೆ ಪ್ಲಸ್ ಇದು ಫ್ರಿಕ್ಷನಲ್ ಫೋರ್ಸ್ ನಮಗೆ ಗೊತ್ತು ಈಸ್ ಮ್ಯೂ ಎನ್. So where this is coefficient of friction, ಅಲ್ಲಿ ಕೊಟ್ಟಿದ್ವಿ 5/12 ಅಂತ. So 5/12 into 50 whole square root of that. If you solve this, you will actually get 54.17 Newton ಬರುತ್ತೆ. ನೋಡಿ ಇಲ್ಲಿ, ಬಟ್ ಸಿನ್ಸ್ ದ ಬ್ಲಾಕ್ ಡಸ್ ನಾಟ್ ಮೂವ್, ಬ್ಲಾಕು ಮೂವ್ ಆಗ್ತಿಲ್ಲ, ಲಿಮಿಟಿಂಗ್ ಫ್ರಿಕ್ಷನ್ ಎಲ್ಲ ಇದೆ ಅಂದರೆ ಅರ್ಥ ಎಫ್ ಈಸ್ ಲೆಸ್ ದೆನ್ ದಿ ಲಿಮಿಟಿಂಗ್ ಫ್ರಿಕ್ಷನಲ್ ಫೋರ್ಸ್. ಸೊ ಹಾಗಾಗಿ ದ ರಿಯಾಕ್ಷನ್ ಇಯರ್ should lie between 50 Newton and 50 whatever the value that we actually got, that is 54 Newton. It is not moving, and therefore ಇಲ್ಲಿ ಕೊಟ್ಟಿರೋ ಆಪ್ಷನ್ಸ್ ಅಲ್ಲಿ ನೋಡಿ nothing is 54 here, 52 ಇದಂತೂ ಆಗಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲ, 52 ಆಗಬೇಕು, and therefore you will actually see option C is the correct option there. So coming to the next problem. A body of mass 5 kg starts from the origin with an initial velocity u is equal to 30 I cap plus 40 j meter per second. So initial velocity is given. if a constant force F is equal to minus I plus 5j Newton acts on the body, the time in which the y component of the velocity becomes 0 is anta ide. So now you can see here, we should only take the y component here. So uy is 40 meter per second, Fi is 5 Newton. So 5 Newton andaga, you know that the force is mass into acceleration. Acceleration g now 10 ತಗೊಂಡಿದ್ದೀವಿ, so 5 into 10. So illi acceleration is Fi divided by m. So 50 divided by the mass 5. This is 1 meter per second square. So Vy is 40 minus illi, we are actually using V is equal to u plus at because I want to find the time here. So idu 0 aito, final velocity. So 40 minus t, so t is equal to 40 seconds, and therefore option C is the correct answer there. So coming to the next problem. A ball of mass m moves with speed v and it strikes normally with a wall and reflects back. If its time of contact with the wall is t, then find the force exerted by the ball on the wall anta ide. So illi force exerted by the ball on the wall is the rate of change of momentum. So we have actually seen that the momentum is conserved situationally. So you have mv minus of, because this is actually coming back, minus of minus madadre, you will have this added, and therefore you have 2 mv divided by t, and therefore the option A is the correct option. So coming to the next problem. A ball of mass 400 gram is dropped from a height of 5 meter. A boy on the ground hits the ball vertically upward, so he is hitting it in the reverse direction with an average force of 100 Newton, so that it attains a vertical height of 20 meters. So with a force 100 Newton alli avanu hodidre, it is going to a height of let us say 20 meter anta kottiyare. The time for which the ball remains in contact with the bat is anta ide. So you need to find out the time. So basically ಇಲ್ಲಿ ಏನಾಗ್ತಿದೆ, ಬ್ಯಾಟ್ ಅಲ್ಲಿ ಹೊಡಿತಿರೋದ್ರಿಂದ huge amount of force is acting for a small interval of time. So ನಾವು ಹೇಳಿದ್ವಿ huge amount of force ಇದ್ರೆ it is basically impulse. Therefore if you actually calculate the impulse for this, so velocity of the ball which is hit by the bat, so v1 in the downward direction is 10 meter per second. So magnitude of the rebound andre ಹೊಡೆದ ಮೇಲೆ ಹೋಗಿದ್ದಾಗ it is negative here because it is moving in the upward direction. In both the cases we have actually used v square is equal to u square plus 2as is use ಮಾಡಿದೀವಿ ನಾವು. So ಇಲ್ಲಿ f is equal to m into dv divided by dt. Thus I told you this is change in momentum. So they have given you the mass minus 20 minus 10 divided by dt. I want dt. Therefore if you solve this, you will be able to see that it is 0.12 second, and the option there is A. So coming to the next problem. A body of mass m at rest explodes into 3 pieces, 2 of which of masses m by 4 each are thrown off in perpendicular directions with velocities 3 meter per second and 4 meter per second respectively. The third piece will be thrown off with a velocity anta keliyare. So you have one mass, adardu 3 ಭಾಗ ಆಗಿದೆ. ಮೊದಲ ಎರಡು will actually have mass m by 4 and m by 4. Together this mass is actually m by 2, and therefore e m mass alli remaining mass will be m by 2 here. Now they are asking you with what velocity this mass is actually moving anta keltiyare. So very simple. So momentum of one piece can be calculated. So which is mass into velocity, m divided by 4 into 3. Momentum of the other piece, m divided by 4 into 4. So the resultant momentum is actually the square root of this 9m square divided by 16 plus m square. This 4 gets cancelled here. So you have 5m divided by 4. So idenidu resultant momentum idu. With the same momentum, the other piece will also actually be flying. Why? Because momentum is basically conserved. The third piece should also have the same momentum. Let its velocity be v anta tagondre. So this you can actually see we are equating this. When you equate this, you will be able to find out. Nodi idu made agutte 2 into 5 into m divided by 4. 2 ones are 2 2s are 4 aaytilli. So it is 5 by 2. So 5 by 2 is 2.5, and therefore the option C is the correct option there. So remember we had actually taken some constrained motion problems there. This is one such problem here. ನಾನು ಆವಾಗಲೇ ಹೇಳಿದ್ದೆ ನಿಮಗೆ ಎರಡು ಮಾಸ್ ಇದೆ ಇಲ್ಲಿ, ಪುಲ್ಲಿ ಒಂದೇ ಇದೆ ಬಟ್ ಈ ಕಡೆ ಇರುವಂಥ ಮಾಸ್ ಎರಡಿದೆ ಇಲ್ಲಿ. ಸೊ ದಿಸ್ ಬಾಡಿ ಶುಡ್ ಆಕ್ಚುಲಿ ಬಿ ಆಕ್ಸಿಲರೇಟಿಂಗ್ ಹಿಯರ್ and this should actually be accelerating in this direction. So, we shall see the 3 equal weights A, B and C. Now, this is equal, but still the net force here is actually greater, of mass 2 kg each, are hanging on a string passing over a fixed frictionless pulley as shown in the figure. The tension in the string connecting the weights B and C anta ide. So, now tension ge formula madidvi already. So, T is equal to 2 m1 m2 divided by, then I told you net force into acceleration due to gravity. So, if you substitute, the answer would actually be 13 Newton, and therefore option B is the correct answer. So, as shown in the figure, 2 equal masses each of 2 kg are suspended from a spring balance. The reading of the spring balance will be 0, 2 kg, 4 kg, between 0 and 2 kg anta ide. Illi nodi, this is a problem like this. Ivaga nanu yavado ondu spring ide, idu attach ಮಾಡಿದೀವಿ ಈ ತರ ಒಂದು ಕಡೆಗೆ, ಇಲ್ಲಿ ಒಂದು ಮಾಸ್ ಅಟ್ಯಾಚ್ ಮಾಡಿದೀವಿ. ಇದರದ್ದು ಫೋರ್ಸ್ ಎಷ್ಟು ಅಂತ ನೋಡಕ್ಕೆ I can just put a weighing machine here, a hanging weighing machine. Then you can actually see this is actually held here. ಇದನ್ನ ನಾನು ಸೀಲಿಂಗ್ ಗೆ ಹಾಕದೆ I can actually hold in my hand also. I can do that. Still, whether you hold it in your hand or whether you are actually fixing it to a ceiling, you are not, this is actually acting like holding that to create the normal force there, so that you can actually measure what is the force acting in the downward direction. And therefore, this mass, or however you are actually holding, or with whatever the force you are actually holding here, would not actually matter to us. So, one of the masses here, illiruva 2 mass alli, one of the mass is actually just like this holding thing that is actually happening there, and therefore the weighing machine would actually show only the 2 kg. So, in this case, the 2 kg weight on the left will act as a support, the left adru irbodu, right adru irbodu, for the spring balance. Hence, its reading will be only 2 kg and nothing else. So, the concept is actually very important in the previous problem. So, coming to this problem, when a force F1, F2, F3 are acting on a particle of mass m such that F2 and F3 are mutually perpendicular, then the particle remains stationary. If the force F2 is now removed, then the acceleration of the particle is option A F1 divided by m, option B F2 F3 divided by m into F1, option C F2 minus F3 divided by m, option D F2 divided by m anta ide. ಇಲ್ಲಿ ನೋಡಿದ್ರೆ ನೋಡಿ, ಈಕ್ವಿಲಿಬ್ರಿಯಂ ಅಲ್ಲಿ ಇರಬೇಕು ಅಂದ್ರೆ this particular force is equal to square root of the other two forces. So, the angle between them is actually equal to 90 degree. So, it is equal to 1 then. Therefore, in the absence of the first force, that is F, the acceleration will be net force divided by the mass. I know this net force is actually given by F2 square plus F3 square divided by m. So, this is nothing but equal to m because the angle here is actually equal to 90, and therefore, the acceleration will be F1 divided by m there. So, the correct option is E A. We shall go to the next problem. A balloon with a mass m is descending down. See, the balloon is they are telling that the balloon, let us say this is the normal for B anta itkolona, mg acting downward direction, idu kelagade bartide anta heltiyare avaru, down with an acceleration a, where a is less than g. How much mass irbeku, how much mass should be removed from it so that it starts moving up with an acceleration a. So, ಇದರಲ್ಲಿ ಎಷ್ಟು ಮಾಸ್ ಆಚೆ ತೆಗೆದುಬಿಟ್ರೆ, ನಾನು ಅದನ್ನು m ಡ್ಯಾಶ್ ಅಂತ ಇಟ್ಕೊಳ್ಳೋಣ, ಎಷ್ಟು ಮಾಸ್ ತೆಗೆದುಬಿಟ್ರೆ ಕೆಳಗಡೆ ಬರೋ ಬದಲು ಇದು ಮೇಲ್ಗಡೆ ಹೋಗುತ್ತೆ ಅಂತ ಪ್ರಶ್ನೆ. ಸೊ, 4 ಆಪ್ಷನ್ ಇದೆ. 2ma divided by g minus a, mg divided by g plus a, ma divided by g minus a, 2ma divided by g plus a ಇದೆ. So, we shall actually see here. ನೋಡಿ, ಇಲ್ಲಿ as I explained you, ಇದರದ್ದು equations of motion ನೋಡಿದ್ರೆ mg acting in the downward direction, ಇದು opposite direction ಇದೆ, which is equal to m into a, call it equation 1. So, ನಾವು ಯಾವ ಮಾಸ್ ಅನ್ನು ಆಚೆ ತೆಗಿಬೇಕು ಅನ್ಕೊಂಡಿದೀವಿ, so that it will actually start moving in the other direction, ಅದನ್ನ m dash ಅಂತ ಕನ್ಸಿಡರ್ ಮಾಡಿದ್ರೆ, you know that b, so same equation here, m minus m dash g is equal to m minus m dash into a, call it equation 2. You remember I had actually said during synopsis, to get the answer, whether to add, subtract, it all depends upon what you want to eliminate there. ಇಲ್ಲಿ ಏನು ತೆಗೆದ್ರೆ ನಿಮಗೆ ಆನ್ಸರ್ ಈಸಿಯಾಗಿ ಸಿಗುತ್ತೆ ಅಂತ. ನನಗೆ ಏನು ಬೇಕೋ ಎಮ್ ಡ್ಯಾಶ್ ಬೇಕೋ, ಅದನ್ನು ಬಿಟ್ಟು ಮಿಕ್ಕಿದ್ದನ್ನೆಲ್ಲ ಕ್ಯಾನ್ಸಲ್ ಮಾಡೋ ಥರ ವಿ ಕ್ಯಾನ್ ಪ್ಲಾನ್. ಅಲ್ಲಿ ಪ್ಲಾನ್ ಮಾಡಿದ್ರೆ ಆ್ಯಡಿಂಗ್ ಇಕ್ವೇಷನ್ 1 and 2 ಮಾಡಿದ್ರೆ ಯು ವಿಲ್ ಸಿ ಬಿ ಕ್ಯಾನ್ಸಲ್ ಆಗುತ್ತೆ. ಅಲ್ಲಿ ಎಮ್ ಡ್ಯಾಶ್ ಜಿ ಇಸ್ ಈಕ್ವಲ್ ಟು 2m ಮೈನಸ್ ಎಮ್ ಡ್ಯಾಶ್ ಇಂಟು ಎ ಆಗುತ್ತೆ. ಸೊ 2ma ಮೈನಸ್ ಎಮ್ ಡ್ಯಾಶ್ ಎ, So if you can see that m dash, that is the mass that has to be taken, is 2 ma divided by g plus a there. So the correct option there as given is D. So we can go to the next problem. A vehicle is in motion with velocity v along a straight horizontal road. If the coefficient of friction between the tires and road is mu, what should be the shortest distance in which the vehicle can stop ಅಂತ ಕೇಳ್ತಿದ್ದಾರೆ. So the final velocity is 0 ಅಂತ ಗೊತ್ತಾಗಿದೆ ನನಗೆ. So we shall see here. ನೋಡಿ ಅದೇ, you can use the equations of motion. V square is equal to u square plus 2as. Final velocity is actually equal to 0. The acceleration is the force, and this force is actually mu into g there. So we will replace that. So you will actually see, I want the distance. Distance is v square divided by 2 mu g, and the correct option given is B there. So this is the correct answer. So shall we move to the next problem? See, a person wants to drive on a vertical surface of large cylindrical wooden wall commonly known as death wall. ಇದನ್ನ ನೀವು ಸರ್ಕಸ್ ಅಲ್ಲೆಲ್ಲ ನೋಡಿರ್ತೀರ, ಈ ಥರ ಒಂದು ಡೆತ್ ವಾಲ್ ಥರ ಇದ್ದು ಇಲ್ಲಿ ಗಾಡಿ ತಗೊಂಡು ಅದರ ಸುತ್ತ ಈಗ ಸುತ್ತಾರೆ. ಆಗ ಸುತ್ತಬೇಕಾದ್ರೆ ಈ ಟೈರು ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ವಾಲ್ಗೆ ಇಲ್ಲಿ ನಾರ್ಮಲ್ ಫೋರ್ಸ್ ಇರುತ್ತೆ, ಇಲ್ಲಿ ಈ ಕಡೆ ಫೋರ್ಸು, ಅಂದರೆ ಅದು ಸುತ್ತಕ್ಕೆ ಯು ನೀಡ್ ಟು ಹ್ಯಾವ್ ದಿ ನೆಸೆಸರಿ ಸೆಂಟ್ರಿಪಿಟಲ್ ಫೋರ್ಸ್. ಸೊ ಎಷ್ಟು ಇನ್ ದಿ ಸರ್ಕಸ್, ದಿ ರೇಡಿಯಸ್ ಆಫ್ ದಿ ವೆಲ್ is r. So radius ಕೊಟ್ಟಿದ್ದಾರೆ, radius of the well r, and the coefficient of friction between the tires and the motorcycle and the wall of the well is mu s. The minimum speed that the motorcyclist must have in order to prevent slipping. So one particular speed ಅಲ್ಲೇ ಹೋಗಬೇಕು. You can calculate the velocity there. You remember during synopsis we actually talked about banking of roads and the minimum velocity required for it to actually negotiate the curve. The car is actually negotiating curve. So it is very similar to that kind of problem. So there are 4 options given here: square root of gr divided by mu s, square root of mu s divided by gr, square root of mu s g divided by r, square root of mu s g r. So we'll see here. See, as I told you, so the normal force is actually in this direction. So mg is acting in this direction. To this there is a friction which is acting in opposite direction. This body is not falling down. Andre ಈ vertical direction ಅಲ್ಲಿ it is not going to move. It is going to move in the horizontal direction. So the n should actually be equal to it should provide the necessary centripetal force, and therefore we have nv square divided by r. So I know this normal force is mu s n, which is equal to m into g. This is from the other equation there. So I am substituting for this n in this particular equation here. So you have mu s into mv square divided by r, which is equal to mg, and therefore v is equal to square root of rg divided by mu s. So the correct option is A. So it's all in how you actually write the equations. ನೀವು ಈಕ್ವೇಷನ್ಸ್ ಕರೆಕ್ಟ್ ಫಸ್ಟ್ ಫ್ರೀ ಬಾಡಿ ಡಯಾಗ್ರಾಮ್ ಬರೆದು ಅದರ ಈಕ್ವೇಷನ್ಸ್ ಅಲ್ಲಿ ಬರೆದ್ಬಿಟ್ರೆ ಇಟ್ ಇಸ್ ವೆರಿ ಈಸಿ ಟು ಸಾಲ್ವ್ ದಿ ಪ್ರಾಬ್ಲಮ್ಸ್ ದೇರ್. ಸೊ ಆಲ್ ದಟ್ ಯು ನೀಡ್ ಟು ಡೂ ಇಸ್ ಯು ಶುಡ್ ಸಿ ವೇರ್ ದ ಬಾಡಿ ಇಸ್ ಆಕ್ಚುಲಿ ಮೂವಿಂಗ್. ಸೊ ಅಂಡ್ ಇನ್ ದಟ್ ಡೈರೆಕ್ಷನ್ ಐ ನೀಡ್ ಟು ಕ್ಯಾಲ್ಕುಲೇಟ್ ವಾಟ್ ಇಸ್ ದಿ ನೆಟ್ ಫೋರ್ಸ್. ಸೊ ನೌ ವಿ ಶಲ್ ಆಕ್ಚುಲಿ ಸಿ ಸಮ್ ಫ್ಯೂ more problems in work energy theorem. Say a body is pushed along straight line by another body applying constant power. The distance moved by the body in time t is proportional to anta keliyare. So now you see, I know power is force into velocity, and this turns out to be a constant. Why? Because this is basically a number. I know that m into force can be written as mass into acceleration, and acceleration is rate of change of velocity, so into v, which is equal to k. So now I am just bringing these two things closer here. So v dv, which is equal to k, ಇದನ್ನು ಈ ಕಡೆ ತಂದಿದ್ದೀನಿ, integral 0 to t dt. So you have v square divided by 2, which is equal to km divided by t. So we move this to this side. So v square is equal to 2 kt divided by m. So v is equal to square root of 2k divided by m, which tells that this is proportional to, if this has to happen, then it is proportional to square root of t. So square root of t can actually be written as t to the power of half. So that distance 0 to x is equal to square root of 2k divided by m, 0 to t. I am replacing this here, t to the power of half dt. So I know that x is proportional to t to the power of 3 by 2. So after taking the integration, you will be able to find out that this is basically t to the power of 3 by 2. So the correct option is actually B. So now going to the next problem. A bullet of mass m moving with velocity v strikes a suspended wooden block of mass m. if the block rises to height h, the initial velocity of the block will be anta keliyare. Options, option A, square root of 2gh, they are simply using v square is equal to v square plus 2gh. Nodi illi B is m plus m divided by m into square root of 2gh, C is m divided by m plus m into 2gh, D is m plus m divided by m into square root of 2gh. So the initial kinetic energy of the block when bullet strikes to it is half mv square. So this is the system mass, the total system though, therefore it is m plus m I though. Due to this kinetic energy block will rise to height h, therefore that height is basically the, when it is raised, it is potential energy, therefore its potential energy is mgh. By conservation of energy, half mv square is equal to the potential energy, because energy need to be conserved, and therefore I can see that these two things actually gets cancelled here. We have v is equal to square root of 2gh, and this is option A. So coming to the next problem, the energy required to accelerate a car for 10 meter per second to 20 meter per second is how many times the energy required to accelerate the car from rest to 10 meter per second. Is it same or different on the question? So we are trying to basically find out the ratio between the kinetic energies. So you can actually say kinetic energy in the first condition is half v2 square minus v1 square. So it was 20 to 10 actually. So it is 159 joules here, and then in the second case you actually see it is half m 10 square minus, I am bringing it from rest and therefore it is 0 square, is it? And then if I take the ratio, you will actually see 50 and then this is 3, and therefore it is 3 times. So the option is D. The correct option is D. So we shall move to the next problem now. See, a bomb of mass 3 mkg explodes into two pieces of masses mkg and 2 mkg. So its velocity of mkg mass is 16 meter per second. The total kinetic energy released in the explosion anta keliyare. So we shall actually see out of these 4 options given here, we will see that by using once again the law of conservation of momentum, initial momentum is equal to the final momentum. So m into 16 is 2m into Vb. Vb is 8 meter per second. So for the system, you actually have this sum of these two kinetic energies, half into m 16 square. You shall just substitute this value of Vb from this, and you will see that it is 192 joules. So the correct option is A. So coming to the next problem. A 1.5 kg block is initially at rest on a horizontal frictionless surface when a horizontal force in the positive direction of x-axis is applied to the back. The force is given by, the force is actually given here, where x is in meter, initial position of the block is x is equal to 0. The minimum kinetic energy of the block between x is equal to 0 to x is equal to 2 meters. So that is where it is actually getting displaced in the whole process. So we need to calculate the energy there. So option A is 2.33 joules, option B 3.33 joules, option C 5.33 joules, option D 6.67 joules anta kottiyare. We will see. So we had this work energy theorem. So work energy, according to work energy theorem, the work done is nothing but the change in the kinetic energy. So using this, it has been displaced from 0 to x. So you integrate to find out how much it has actually changed it. So now we will actually see that for k to be maximum, dk by dx should actually be equal to 0. So 4 minus x square is equal to 0, or x is equal to plus or minus 2 meters. So now they have given you it is going up to 2. So x is equal to plus 2 meters ಇದೆ. ಅಂದ್ರೆ ಇದರದು ಸೆಕೆಂಡ್ ಡೆರಿವೇಟಿವ್ ಏನಾಗುತ್ತೆ, ಇಲ್ಲಿ ಇದರ ಸೆಕೆಂಡ್ ಡೆರಿವೇಟಿವ್ ತಗೊಂಡ್ರೆ it will actually become negative. So the kinetic energy is maximum. So k max is actually equal to this, and this turns out to be that it is 5.33 joules. So option C is the correct answer. So this is a graphical question. The graph between resistive force F acting on a body and the distance covered by the body is shown in the figure. The mass of the body is 25 kg and initial velocity is 2 meter per second. When the distance covered by the body is 4 meter, its kinetic energy would be, they are asking you to calculate the kinetic energy. You see the graph clearly. Initial kinetic energy of the body is, I know, is half mv square. which is half into mass of the body is given to be 25 into velocity 2 square, which is 4. So it is 50 joules. So work done against the resistive force is nothing but the area under this particular curve. Whatever is the area there, that is what is has to be calculated. So half into base into height, that's what has actually been done here. So that turns out to be 40 joules. So I know that work done is final kinetic energy minus initial kinetic energy. So final kinetic energy is initial kinetic energy minus work done. So this is 50 minus 40, so which is 10 joules, and therefore option D is the correct answer. So moving on to the next question. A block of mass m moving at a speed of a collides with another block of mass 2m at rest. The lighter block comes to rest after the collision. The coefficient of restitution anta keltiyare. So we will actually see here. I know that from law of conservation of momentum, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Substituting these values of masses and velocities here, we will figure out that v2 is equal to u divided by 2. So they have given you C, this coefficient of restitution denoted by E. This should actually be E. So we had seen this particular formula during synopsis. So the ratios of the velocities, v2 minus v1 divided by u1 minus u2. So this is u2. So you will actually see this turns out to be 0.5, and the option is C here. Next problem. A body of mass 2 kg travelling at 4 meter per second makes a head-on collision with a body of mass 1 kg travelling in the opposite direction with a velocity of 2 meter per second. The velocities of two bodies after collision anta keliyare. So we need to find out the velocities of other two bodies here. So once again we actually use the law of conservation of momentum here. Substituting this, you will actually see v2 is equal to 6 minus 2v. But momentum conservation agide andre kinetic energy of the system also should actually be conserved. So we take the kinetic energy of all this particular velocities. Then you actually see, substituting, you get an equation here. Solving, you will see v1 is equal to 0 or v1 is equal to 4 here. When v1 is equal to 0, so v1 is equal to, so in this particular quadratic equation, we actually get v1 is equal to 0 or v1 is equal to 4. Now let us say we substitute v1 is equal to 0. Then what will happen to v2, which is actually 6. But now let us say if you substitute v1 is equal to 4, v2 turns out to be minus 2. And if you actually see in the previous slide, we don't have that option here. And then it turns out that this, when v is equal to 0, v2 is equal to 6 meter per second is actually the correct option. And therefore answer is C there. So a particle accelerating uniformly has velocity v at time t. What is the work done in time t anta keliyare. So you have the options given there. Half mv square divided by t1 square into t square, half mv divided by t1 into t square, mv square divided by t1 square into t square, 2 mv square divided by t1 square into t square. You will actually see velocity of the particle accelerating uniformly in time t1, v is equal to from v is equal to u plus at. We know that v is equal to at1. So I know a is equal to v divided by t1. Velocity of the particle in time t. So that change we will actually call it as v dash. So which is equal to vt divided by t1, because I have substituted the value of a here in this particular case. Now from work energy theorem, I know work done is change in the kinetic energy, and therefore the final kinetic energy minus the initial kinetic energy is half m. I am substituting for this value of v1 dash from this, and you will actually see this is half m v square divided by t1 square into t square, and therefore option A is the correct answer. A sphere of mass m moving with velocity v enters a hanging bag of sand. So you have a hanging bag of sand and you have a sphere which is actually thrown here of some mass with some velocity v here. So then if the mass of the bag m is raised to height h, so illinda illi move madide, it raised to some height h, then the velocity of the sphere anta keltiyare. So what is the velocity? What is this velocity is the question here. So we will actually see here. By the law of conservation of linear momentum, initial momentum of the sphere is equal to final momentum of the system. So you have these two masses and the velocity of the system here. If the system rises to height h, then by the conservation of energy, kinetic energy should be equal to the potential energy. Kinetic energy is equal to the potential energy. So, V of the system is equal to square root of 2 GH, and therefore, option A is the correct answer. So, now coming to the next problem. A body is thrown vertically up with certain initial velocity. The potential and kinetic energies of the body are equal at a point P in its path. If the same body is thrown with double the velocity upwards, the ratio of potential and kinetic energies of the body when it crosses the same point anta keltiyare. So, illi nodi first case alli at a point P, its kinetic and potential energies are actually equal, and therefore equating this kinetic and potential energies at this particular height, we know that it is V square divided by 2h. So, in the second case, it is the body's velocity is twice the velocity as in the case of the initial, but at the same point. That is very important there. So, taking the ratios of potential energy and kinetic energy, you will figure out that this turns out to be equal to 1 by 4, and the correct option is actually B there. So, coming to the next problem. A stationary particle explodes into two particles of masses m1 and m2 which move in opposite directions with velocities v1 and v2. The ratios of their kinetic energies is E1, E2 is and the KLS. So, you need to calculate the ratios of the kinetic energies. So, from the law of conservation of energy, initial momentum is equal to final momentum. Using this, I know the ratios of the two velocities v1 and v2, which is equal to m2 divided by m1. Thus, the ratios of kinetic energies. So, here the energy that is given is actually kinetic energy, and therefore half m1 v1 square. So, but I know what is v1 and v2 here, which is m2 divided by m1. Substitute here, you will actually see the correct option is basically C there. So, coming to the next problem. A stationary bomb explodes into two parts of masses in the ratio 1:3. If the heavier mass moves with a velocity 4 meter per second, what is the velocity of the lighter part? So, the options there are 12 meter per second opposite to heavier mass, 12 meter per second in the direction of the heavier mass, 6 meter per second opposite to heavier mass, 6 meter per second in the direction of the heavier mass. So, we will actually see here the ratios of the mass is given to be 1:3. Therefore, let us say m1 is some x kg, and therefore m2 is 3x kg. So, now using the law of conservation of momentum, you will see that the m1 v1 plus m2 v2 is equal to 0. I am substituting these values. You will see v1 is equal to minus 12 meter per second. Minus sign tells you that the velocity of the lighter mass is opposite to that of the heavier mass, and therefore the correct option turns out to be A there. And now we have actually seen these many examples here. So, based on these examples, you will be able to correlate these ideas here and then work out some more problems, so that you will actually be able to do well in the competitive examinations. So, thank you for watching this.